All right, so like I was saying, electrical electronic components, we'll jump right in. The first lesson is going to be if you're going to work on the car and you need to look at wiring diagrams, somewhere in that service manual, you're going to get a key for diagrams like this. So I just pulled a screenshot of one. For the most part, the symbols are similar enough where if you learn one symbol and then let's say this is a Toyota symbol and then you jump on a Ford, probably the symbols will be pretty similar, but once in a while you'll jump on something like European and it'll be like, whoa, what the heck symbol is that? Just so you know, you don't have to memorize every symbol. Somewhere in that service manual there'll be a key where you can actually look up what each one of them means. And then it's very common as well for unique things to be labeled. So like for example, this right here, the cigarette lighter, that symbol is kind of weird to me. It's sort of like, what is that? I don't know if that's a video camera or like a horn or something. So on a lot of the newer diagrams, they'll actually name that. And in some of the European stuff, which is kind of weird, they may not have a name for it, but they'll have like a way to identify it. Like if a module is, let's say, the rear area module, they may call that the R27. And so if people are talking about the rear area module, they may be like, oh, it's R27. R27 is telling you that it's the rear area module. So the symbols are common, but also sometimes they're labeled too. So like one of the first ones would be switches. If you guys think about what the purpose of a switch is, we're using a switch to control the circuit. So if we want to control the circuit, be able to turn the circuit on or off, we would go with a switch. But what if we wanted to protect a circuit, make sure the wires don't burn up? Would a switch do that? What type of thing could we use to protect a circuit? It'd be next, like fuses, circuit breakers, right? So all these have a role in the circuit to make it do something. Protect the circuit, control the circuit, modify the current flow. Like maybe we don't want too much current flow, we may put a resistor in there and that way it's going to reduce the current flow. And the resistor also consume voltage, right? So all these things are there for a reason. And so when the electrical engineers design the circuit or the vehicle or whatever, they can use any one of these different components to have the circuit do what they want it to do. Cool. And so if you look like various control devices, I think most of us by now would understand a switch, but did you know switches can be normally open or normally closed? Normally open would mean the switch is not making connection unless you go do something to it, right? So this first one right here, that's a normally open. Normally open is probably the more common. So if you were to think a horn, you ever beep the horn? You wouldn't do that. Why would you do that? There's no reason. That's uncalled for. But if you did beep the horn, would you agree the horn switch you'd expect to be normally open? Normally open means it's not going to send the voltage to the horn until you close it. What if it was the other way around? What if the horn was normally closed? It'd be blowing the horn all the time and you'd have to press it to open it, which would stop it. That'd be kind of crazy, right? So it's a little gruesome perhaps, but you guys ever heard of like the dead man switch? So if somebody were to, be holding a switch, to do some sort of, let's say, a hostage negotiation situation, they'll hold the switch, and then like they say, hey, if you shoot me or take me out or whatever, I'm going to let go of the switch. It's going to blow this bomb up or something. That would actually, depending on the exact type, maybe that's a normally closed switch. And when they release it, it opens up and that triggers some sort of a, explosion or something in Hollywood. So, or another example may be if you had, let's say you went out jet skiing, and you ever notice like with boats or jet skis, sometimes they have a little kill switch. It's not exactly a key, but there's a thing that's going to press a switch down and then you're going to tether it to your body. If you press the switch down, that switch is going to stay closed, but the second that you fall off the back of the jet ski, it's going to open it, or it could go the other way around, right? So sometimes we want normally open, sometimes we want a normally closed. An automotive specific example would be, you guys like air conditioning? Air conditioning, a lot of times we'll use a normally closed switch. It may be like the high side pressure cutoff switch. So if you're running AC and everything is cool, you don't have too much pressure. But if for some reason maybe the system is overcharged, or maybe there's some massive restriction in the piping or something, the high side pressure will go so high, the excessive pressure will actually open a normally closed switch, and when it opens it, it interrupts the power going to the compressor and disables the AC. So that's an example of like a normally closed switch on a vehicle that's there for safety purposes, right? So how do you know if they're normally open or normally closed? You just look at the diagram. You see how that one's open? That's normally open. This one's closed, that's normally closed. You just need to know when you go to test it. You know, if a horn switch is normally open and you want to test the switch, logically you're going to probably have to close it, which means when you go to test the horn switch, you're going to have to press the pad in the middle for the horn. Make sense? Not really complex. And then if you look at relays, I feel like is the next logical thing to cover. If you look at these relays, that's a normally open relay. So look at the right side of that relay. That one is open. We would test this switch of this relay the same. There should be no continuity until we close it, at which point we should have good continuity. We have tons of relays. So let's say, one second. Matcha, don't judge me. How about a fuel pump? If we want to run a fuel pump, we generally want the fuel pump to be controlled by the computer. The computer is going to have a very hard time handling the 15 or so amps a fuel pump's going to draw. So we'll have a computer control this side of the relay. This left side we're going to cover right now. And this left side ultimately controls the right side, which is where the high current flows. So over here you might have 15 amps. The computer is not going to play nice with that. But over here you might have a quarter of an amp. The computer's going to control that really well. So if I were to explain this relay, we got to jump down to solenoids. But first, look at the switch side. The switch is just opened or closed, right? So just like a normal switch, if a switch is open and you want to send current to the fuel pump, you need to close the switch. And in your mind, you're thinking, oh, we need to go in here and actually press it. But see, we want the computer, or, you know, we'll say the computer to make it simple. We want the computer to be able to open or close that switch, which is why we don't use a switch. We use a relay, and the relay has a switch in it, but this coil right here, which is like a solenoid, is going to actually control the switch. So now that's where I jump down here. What a solenoid does, when we send 12 volts through a solenoid and we have ground on the other side, it makes a magnetic field, and that's why there's these little loops. These are the windings. So if we send current through here, it magnetizes the solenoid. Now, I mentioned that in the introduction. The visual one is like the door locks, right? If you energize the solenoid, it goes thunk and it locks the doors. And then if you reverse the polarity, you know, there's different ways to do it. That solenoid can actually open or close or lock or unlock. However, on a relay, we've got the solenoid right here. If we send 12 volts and ground, it will actually magnetize and it'll grab this switch and pull it over to the left. If it pulls the switch over to the left and now it makes a contact, can you see how the solenoid just closed the switch for us? So that's what a relay does. We use a solenoid on the control side, and I call it the control side because it controls the relay, right? So The relay, if you think about it, everybody knows relays, oh, they click. Well, yeah, they click when you have 12 volts and ground on the control side, and that should magnetize and pull the switching contactor over, and that's the click a relay makes. But by the time the relay clicks, that should let 12 volts that was trying to go into the relay actually go through the now closed switch, and that 12 volts should go to the fuel pump or to the AC compressor or to the whatever the heck you want to control. We use these in horns, all sorts of stuff.
So after it goes through, does it go back to open again because it's gone, the voltage is left?
So that's, if you look at the left side, anytime the left side has 12 volts and ground, this switch is closed. And when this switch is closed, we're usually sending bigger power, 15 amps, down to the fuel pump. It'll continue to send 15 amps down to the fuel pump as long as we have 12 volts and ground here, right? So if I were to extract this relay and throw it into a diagram, maybe what we do is we give 12 volts to the coil and we give 12 volts to the switch side. And then on the switch side, it goes down to the fuel pump to give the fuel pump power. But on the control side, maybe we wire this into the ECM, and all the ECM has to do is give ground or not give ground. If the ECM gives ground, this goes wong, and it makes it switch over, and it powers the fuel pump. Free sound effects for you. But then if the ECM takes the ground away, it no longer magnetizes, and yes, this will spring back open, and the fuel pump will shut off. So the relay is a great way to use what we call a low current on the left side to control a high current on the right side. If it's low current, low amps, that means we can use little tiny wires, we can use a module, we can control that really easily. But on the right side, the high current, that's going to be like a bigger, a 15 amp wire, like a 12 gauge wire or something. Right, we can't be running huge wires through the ECM. The ECM's made for little low current electronic stuff. Cool, so the normally open relay is by far the most common. This relay will sit there and not power the thing, the fuel pump, until it gets 12 volts and ground on the control side, and then it'll power the fuel pump. That's normal. There's some exceptions though. Like for example, maybe it's an anti-theft system that, if you go to start the car, this should be normally closed, but if it detects that you don't have the correct key or something, the ECM can give 12 volts and ground, which will force the relay open, which will stop power from getting to the starter, and therefore you can't steal the car, right? So there's some instances where we may want a normally closed relay that we have to actually force open for something, to interrupt power, to interrupt somebody from starting the car and stealing it, right? So kind of makes sense on those, sort of, right? Because we're going to apply these in the circuit, but if you at least understand right now your goal is switches, we have to open and close those with action, with our hands and fingers and arms and stuff. Solenoids, if we give 12 volts and ground, they magnetize, and we can do a lot of stuff with that, a bunch of stuff. Relays combine a solenoid with a switch. The solenoid controls the open and closing of the switch. Nobody has to touch that. A computer can do that, right? And then we're going to get into diodes. Who's heard of a diode before? I guarantee you have. Who's heard of an LED before? So you've all heard of a diode. An LED is nothing more than a light-emitting diode. The diode, we'll say most simply, it's actually explained in how it looks. That's going to be a one-way check valve for electrons, we'll say. So if you look at this, see how it's pointing to the left? It's saying, hey, electrons, you can go left, but you can't go right. So there's various reasons we may want a diode, but generally just a diode would be probably inside of a module, inside of a computer or something. It's pretty rare that you actually locate a diode that you can service. They're mostly in the electronic circuit board. There's some exceptions. Maybe an AC compressor may have a diode, and part of the reason why is when we're engaging and disengaging the AC compressor, sometimes we make a voltage spike. And so what we'll do is we'll put a diode in there that will allow electrons to go down to the AC compressor clutch relay. But when we're engaging and disengaging it, it makes the voltage spike. The diode would prevent it from coming back in and spiking into the ECM. And some of those diodes are actually external. So that'd be like an AC compressor clutch diode. Okay, makes sense? Just a check valve. One way, yes. The other way, no. Then as we get a little more into there, diodes, actually they have different types. They have some diodes that as long as it's above a certain voltage, it'll let it flow both ways. Or if it's below a certain voltage, it won't. And there's some finer points there. And then we'll sneak over to capacitor. Anybody heard of a capacitor? We know you're into car audio if you know what a capacitor is. So that's probably the most logical way that I'll explain it. If you're running big old subwoofers, when how could I say, when the beat drops, all of a sudden the subwoofers, that draws a lot of power from the system. So if you have your alternators working as hard as it can and it's making 13.9 volts, and then all of a sudden the beat drops and the alternator can't keep up, it may go down 13.2, 12.7, 12.5. Like at that point, you're no longer able to really charge your battery. If your voltage drops from 13.9 to 12.5, you'll visibly see the lights dim in the car. Electronic accessories may start to malfunction. So if every time the beat drops, your lights go dim and stuff, you think that's going to be acceptable to most drivers? They're going to think that you're flashing the high beams every time you got the boom boom kicking in, right? So one of the ways that we can, let's say, mitigate that, we can solve that, is a capacitor. A capacitor will grab excess electricity and hold it when there's a surplus. But then when we're running a little short, when the beat drops, the capacitor will put it back out there. It's kind of like a buffer. When you guys go to load YouTube, and a lot of times it'll buffer for a second. The buffer is making sure it's got enough of the video loaded so it's smooth, it's not choppy. Same type of thing. The capacitor will make it so that the voltage isn't up and down really rough. The capacitor will absorb the highs and supplement the lows and make it a little more smooth. That's what a capacitor does. But we can apply this in other ways as well. So let's say, for example, sometimes they say things that are a little extreme to make sure you understand. You were driving down, no, it's not you. Somebody else was driving down the road. They got into an accident. They got hit so hard by this tractor trailer, it blew the battery right out of the car. Your battery's gone. It's down the road. And it happened in a split second. You still want your airbags to work, right? How are your airbags going to deploy when they needed the 12 volts from the battery that's down the road? Bingo. So they put capacitors in the airbag module, and actually the capacitor contains enough electricity to fire the airbags, even if the electrical system is damaged or something, right? So there's good things about capacitors for safety. The negative is, I'll tell you, if you understood what I just said, normally when you want to disable airbags from deploying, you disconnect the battery and you're like, oh, the airbags can't deploy because the battery's disconnected. Well, wait a minute, there's capacitors in there. So a lot of times that's why in service information it'll tell you, disconnect the battery and then wait this long, 10 minutes, 30 seconds, 1 minute, whatever. The service manual will specify based on the size of that capacitor, how long you have to wait before you start probing around and you accidentally trigger an airbag deployment. Makes sense? So capacitors are used in that function. And then, and we'll cover some of these a couple times because they can be a little complicated. But for example, a transistor, let's just say, we'll go with an NPN type. A transistor is just like a relay, like this, right? We can have the low current side control the high current side. So the computer likes to control the left, and the right does big work, heavy work, high current work. This transistor is what I would like to say is a solid state relay. And you're like, what the heck's that mean? Well, a relay has moving parts, right? There's physical movement, so therefore it's not solid state. When I say solid state, what that means is it's using electronics. For example, an NPN junction. Okay, so here's how they're the same. The base right here is very low current. A computer can easily control the base. So if we were to have, let's say, we're trying to flow electrons through here, that would be the high current. This could power a fuel pump. We have 12 volts, we send it into this transistor, and if the transistor is activated, it will send 12 volts to the fuel pump and run the pump. But how do we control the transistor? Well, it's all about what it gets right here on the base. So if it's an NPN, when we give positive right here, that's going to make it so that electrons will flow through. A lot of times this would be on the ground side, right? So the second that we give positive voltage here from the ECM, it can just be very low current, a little bit of positive, boom, now we'll actually have current flowing through the high current side of the transistor, right? And just similarly, it's going to be a PNP is going to be just applying a ground right here, right? So this one applied a positive, and this one applied a ground. For you, honestly, it doesn't really matter. The only time I really think about this is when I teach this class. If I'm diagnosing something, this transistor is inside the ECU, I don't really care if it's an NPN or a PNP. What I care about is the ECM giving it what it needs to have current flow, right? So if the power source is inside the ECM and then coming out of the ECM, we should have this, and that should power the fuel pump. I go to the ECM and I'd say like, hey, are you giving me the power that the fuel pump needs? Yes or no? And if I probe right here and it's supposed to be giving me, let's say 12 volts right here, if I don't have 12 volts right here, I'm suspecting maybe this transistor is no good. But what I would need to do typically is go in with a scan tool, and I could go in the scan tool and I could go into like active test, special functions, some special menu, and then go like control the fuel pump, turn the fuel pump on, click. When I tell the scan tool to tell the ECM to turn the fuel pump on, what it's actually doing is it's talking with the ECM and saying, hey, give a positive right there on that base. So if I want to test it, I got to tell the computer, turn that fuel pump on, which means the integrated chip is going to give a positive right here. And then I can use my meter to measure right here, which is outside the ECM, and be like, is this transistor providing power for the fuel pump or not? Kind of make sense? And if I command it to provide power and I go over here and it's still not providing power, I could reasonably say like, hey, this has a bad transistor. At that point, what do you think I would do if it's got a bad transistor? I told you this once. We don't replace transistors. You're going to be like, oh, it's got a bad transistor, which means it's got a bad ECU, which means price the ECU, get an estimate on it. So you remember we started with strategy-based diagnosis, right? Remember how we were trying to say you don't want to be like, oh, your car doesn't start, the fuel pump's not pumping, let's start with the fuel pump. You want to see, is the fuel pump getting the voltage? And is the fuel pump getting the voltage from the ECU where it's supposed to get it? And it's very possible that the fuel pump's getting the voltage and the fuel pump's bad. Or it's also possible that the fuel pump's not getting the voltage and the wiring has a problem. But it's also, however, less likely, but also still possible that the fuel pump's not getting voltage because the ECM isn't providing voltage because this transistor's burned out. Make sense? And that's what's really going to separate like the entry level from the professional, is when you don't have to throw 2 or 3 parts at it before you figure out the ECM is bad. You'd be able to measure at the ECM, be like, oh, this ECM's not putting out voltage. I suspect the transistor. Let me make sure I command it on with the scan tool. It still doesn't put out voltage. Uh-oh. Makes sense? So in your story, you'd be specifically saying like, They may not always call it a transistor. Sometimes they'll call it a driver. Be like, oh, it's got an open driver in the ECU for the fuel pump. And if I read that on a write-up, I'd be like, okay, this person tested some stuff. And in your story, you might even say, I tested for voltage right here, and that may be at terminal 72 of the ECM, and it had 0 volts, right? So that's how we're really linking like the strategy-based diagnosis to fix it right the first time to how. You got to understand how the circuit works, and you got to actually measure it and test it, not just roll out with the parts cannon, just replacing stuff. Okay, so that's an overview of some of the control devices. Don't worry, we still got some more things. I feel like this will probably be fairly easy for you to understand now that we've applied it. You got this thing, by the way, that's a battery. The battery symbol can vary. This, for example, is a battery symbol, but they do vary. It can look different. Obviously, the battery's got connected to chassis ground. It comes out of the positive. It sends it up through, like in this case, we're showing you protection devices. It goes through a circuit breaker. Do you remember what a circuit breaker is compared to a fuse? Circuit breaker trips, fuse blows. Circuit breaker, you can reset it. Fuse, you throw it in the garbage, you get another one, you put it in there. Makes sense? There's no reason to have both of these here. This is just an example to show you. We're going to have some sort of a circuit protection device. Right, and from there, it goes to the switch. Now you understand what's the purpose of the switch in this circuit. It's a C word. It does something for this light bulb. What's it do for this light bulb?
Controls the load?
Yeah, that's it. It controls it. That's right. The switch just controls the circuit, so that's a form of control. So these over here are protection devices. This is a control device. This is a load. Now, in this case, the load's a light bulb, but, you know, technically, I've already yanked this apart. This is the load in a circuit, the starter circuit. This is the thing that does the work. So the resistance that's designed into the circuit will be right here, and it'll make this motor turn, and this motor will actually engage your flywheel or flex plate and start the engine, right? So don't think of the load as just a bulb. The load could be a solenoid, a motor, a resistor, a bulb, all sorts of stuff. Cool. And then just as a side note, this is actually a diode, and you'll notice the diode has a symbol on it because it's what we call polarity sensitive. So if it's this type of a bulb, you could put that bulb in either way. But if it's an LED on a car, a lot of times those have to be installed a certain way. And if it's like a car that came with LEDs, they'll probably make the connector so you can't put it backwards. But if you change your regular incandescent style bulb to LEDs, actually you can probably put it in backwards and just won't work. Because remember, the diode is a one-way check valve, like a gate. So sometimes you got to look on the part, like this diode, for example, and make sure you put it in the right direction. Cool, just a little bonus. And so if we talk about switches, remember they turn things on and off. Some switches are more advanced than others, but basically if the switch is turned off, generally that's going to mean it's open. So I like to call the switch open. You may call the switch off. The reason I would suggest open is because if you visualize it as open, you can see that the voltage will come in and then it'll stop right there because it's open. But you could switch open with off, and then closed would be on, right? Sometimes we switch those. But most technicians are going to say open or closed because that's how you'd visualize it when you're diagnosing it. Okay, and then let's say we've got, for example, toggle switches. A toggle switch is toggles on or off. So if it's a toggle switch, you push it up and it's on, or you push it down and it's off. That's kind of like your basic light switch in the house. But we also have push button switches. The example of that would be like the horn switch, right? That's a push button switch. When you press the horn, you don't toggle it on and leave it on until you're done trying to upset the people in front of you, and then you turn it back off, right? It's momentary. You have to press and hold it for as long as you want it to remain closed. That's an example of a push button. And then if you get into, let's say, this type of switch, that we'll call like a multi-purpose switch or a specialty switch, that can have all sorts of stuff going on. So technically, just this turn signal switch alone has the headlights, it has the windshield washer, the windshield wipers, sometimes the turn signals. There may be no less than 10 different switches inside of that switch assembly. So what's kind of annoying in automotive is, let's say that you had a problem with the windshield washer pump and you press this and you diagnose that this part of the switch is no good. You got to replace this whole entire switch. It's hard to diagnose these because it's not just like 2 wires. Like there's 20 wires going into this thing. So how are you going to know which 2 wires control the washer pump? You're all over the wiring diagram. You're like, it's this terminal and this terminal. And if you can understand and get to that point, actually diagnosing this type of switch is the same as any type of switch, right? So on the diagram, it could look really simple like this. But later you'll see, especially when we get into actually wiring diagrams, when it's one of those multifunction switches, it gets very complex very quickly. And you're like, whoa, what's going on there? There's a whole bunch of stuff. So we got to build up to that. All right, so like for example, now you can see what's the status of this switch. Closed or on? Closed or on. Yeah, exactly. That's right. That's why the light bulb is on, because we're sending current through the load, through the bulb. All right. And that's just kind of what I was saying about the switches can be very, very complex. So if you look at a wiring diagram, there's your a multifunction switch. So if, let's say, you were trying to diagnose that switch, you have to say like, well, which one am I really worried about? If the customer's concern is my headlights don't work, I don't really want you or any technician to go in and test all these switches, right? There's a lot of micro switches within the one big switch assembly. If it's a headlight issue, I'd focus more over here. This has 12 volts coming in, so I could make sure I get 12 volts here. If I don't get 12 volts here, it's probably up in the fuse box. Maybe I could check the fuse, right? But if I've got voltage coming in here, how should I test this switch for headlight operation? I actually have to turn the switch to the headlight position. So if you have the switch in the off position, you have 12 volts coming in. You're not going to have 12 volts going out because it's a normally open switch. So you have to actually turn it to the headlight position, or let's say like in this case, the parking lamp position, and then you can't go inside the switch. You can only test right here at the outside of the box. So you'd be like, I got 12 volts coming in, I put it in parking lamps, and I don't have 12 volts coming out. That's because there's an open in here. But if 12 volts made it to here, and 12 volts never made it out, and I'm sure the switch is in the right position, we just diagnose that it's got a bad switch, right? But you're not replacing just this part. You're replacing everything in this box, and it's going to look like this. Kind of makes sense? So generally, no, you'd go to like the connector. So I don't have a headlight switch, but I've got this ABS unit. There's a connector right here. You could actually probe here to make sure you have voltage coming in, and then here to make sure you have voltage going out. But to get to that point, you got to know which wire is which and which location it's in so you can test them at the right point. But these are generally not made to be taken apart. We can go right to it where we can disconnect it and reconnect it, and there's a connector there, and we can do some back probing and stuff. But when you guys learn on the board, you're going to start with stuff like this to get the concept, and we're going to work our way toward, on the car, you're looking at something more like this, and there's 40 wires going in, and you got to make sure you're on the right terminal when you do the test. So there's building up to that point. It takes a little time. Cool, and then like here's an example of another type of switch. You can see these switches can can pretty quickly get to be a little bit complicated. But the ideas are still the same. Normally open. This one actually may be normally closed. See, normal is to the left. It's normally closed in a way if this is closed, but then if you force it open, it's going to go over to here, right? So there's 1, 2, 3, 4, 5, 6, 7, 8 switches in there. You got another bunch of them in here, right? So understanding these is going to take a little time, but just so you know, those are all switches. And that's the control part of the circuit. Now, when we get into the protection part of the circuit, a lot of words, but I'll just show you the picture. Fuses. Different types of fuses. One fuse type can't replace another fuse type. There's a certain like spacing in the fuse box. So if you had this maxi fuse, and let's say the maxi fuse is over here, and the maxi fuse blew, you can't just throw a regular fuse in there, right? So we've got a maxi fuse. These are Pacific fuses. They just a lot of times call this an automotive type of fuse, a glass fuse, a mini automotive fuse, a micro automotive fuse. They even have these in low profile. They've got like a whole assortment of fuses all in the fuse box. And so they've even got, I'm seeing more commonly, fuses like this that are doubled up, because this fuse box, we only have so much real estate. And if we start to run out of room, it's like, how are we going to do this? They've made the fuses smaller, smaller, smaller. Now they're about as small as they can be. And we've started to have to combine them and double them up and do weird stuff. I see where like one will feed the center, and then there's a fuse element to the right and a fuse element to the left, but it's all in one fuse assembly just to save space. It's gotten kind of excessive, I would say, but ultimately, if I show you how to test the fuse and you can test the fuse and the fuse is no good, then it's as simple as making sure you can get the right type of fuse and replace it. Now that brings up another point that we won't solve today, but I'll just make sure you understand. If the fuse blew, something caused the fuse to blow. So let's say the most common, you know where you plug your cell phone charger, and you plug your cell phone charger in a little power outlet. It used to be the cigarette lighter. You plug that in, and if periodically it blows the fuse, the problem could be in the vehicle side. But what's pretty common with those cell phone chargers is, you know, they have some wire like this, and the wire flexes, and you put it in your pocket and it flexes, and eventually inside it might break a little bit and it could short out. It might not blow the fuse today, it might blow the fuse next week, and then poof, your fuse is blown. So if you find that the fuse is blown, there's nothing really wrong with putting a fuse in, just pulling the fuse out, putting the fuse in. If it fixes it, great. But if you pull the fuse out and you put a new fuse in and it blows it instantly, you can keep doing that over and over until you burned up all your fuses and now you have no more fuses. It needs to be diagnosed, okay? So fuses should not be blowing like that. If it's the phone charger and you put the new fuse in and you flex the phone charger and you hear pow and the fuse blows, you're like, oh, it's the charger. Throw it in the trash, all the way in the trash. Because if you give it to somebody and they're like, oh yeah, I'll take it, and then it causes an intermittent fuse blowing, they could be kind of hard to track it down, okay? So if you diagnose it as the phone charger, throw it in the garbage. But some of the things are not that simple. Like if it's a fuel pump fuse that's blowing, it could be in the wiring, it could be in the pump. If it's any number of things, the windshield washer blows the fuse. I've seen where, you know, a little wire gets rubbed through and it shorts to ground intermittently when you hit a bump, and bang, the fuse is blown, right? So for right now, that's all short diagnosis. For right now, we're just talking about the fuses, how to test them, not necessarily how to diagnose the root cause of why the fuse blew, okay? So don't be confused here. You got all sorts of different types. This fuse, medium current fuse, high current fuse, fusible link, this one we're going to pause on. Fusible links, in my opinion, are the worst. And the reason why, all these so far, you could grab pliers and rip them out of the fuse box, like this. Just yank them out and put a new one in. Fusible link, doesn't that just look like a wire? That's pretty much what a fusible link is. You'll have regular wire, and then when they need to put a fuse in, but there's no room or something, they'll just cut a section of the wire out, and they'll put in a smaller size wire with a very gummy insulation. And if you think about it, if that's the smallest part of the wire, that's the part that would fail. So they're basically purposely letting the smallest section of the wire burn up. And the way that you test them, you could test some of these with your meter, but the way you test a fusible link, actually, you grab the wire like this and you pull on it. And if it's a wire inside, you feel it's like tight. But if it's a fusible link and the wire has burned up, all that's left is the gummy insulation. It'll be like, you'd be like, oh, that fusible link is bad. But now what do you have to do to fix it? Yeah, so sometimes you have to replace the whole cable. Other times you can actually cut it and splice something in, but you don't just get to yank it out and put a new thing in with pliers. So that's part of the reason I'd say fusible links are kind of dumb. I don't like them. It's a cheap way to do it. I'd rather run it up into the fuse box and use like a maxi fuse or something.
Do they always have that clip on it?
Not necessarily, but this is actually pretty accurate. This is probably connected to the battery, and then it's got this little spot where the big wire is spliced to the small fusible link wire, and another one. So they'll usually have some sort of connection looking thing, and then in the middle, this will be like just a little bit of a different looking type of insulation, more rubbery, thicker, kind of weird. But you know, in fairness though, they're less and less common. They were pretty common on older cars, especially right there at the battery. It'd usually be if something's a major component, like they might have a fusible link for the alternator or something, because they didn't want to run big wires up through the fuse box. So I bet you will see them. And then the circuit breaker, I should specify, circuit breakers can always be reset, but sometimes they reset themselves, which is cool. So that would be like a PTC breaker, positive temperature coefficient. For example, I'm going to say if you have kids, but let's be real, some of this could be us too. You get in the car and you put the windows up and you put them down, and you put them up and you put them down, and up and down and up and down and up and down, and all of a sudden they stop working, and you're like, uh-oh, what happened? Give it a minute and they'll start working again, up and down, up and down. That is due to a PTC circuit breaker. As you go up and down and up and down, you know, the temperature of that motor can get a little bit hot, and that can be more mechanical resistance, which can actually increase current, and you might actually trip the circuit breaker. But this is sort of like two pieces of metal. When the two pieces of metal get hot, they separate, and now there's no contact. But if you give them time with not running the windows, they cool down and cool down and cool down, and then they touch, and now the windows work again. Okay, so sometimes with things like power seats, power windows, power locks sometimes, something that could potentially be overheated, or, you know, like maybe you leave California and you go an icy place. You go someplace where ice is very prevalent, and maybe it's the Great Lakes, and the Great Lakes has got this wind blowing off the lakes, and it freezes the whole side of your car, and you go to try to run the windows or try to run your wipers, and they're frozen. That can actually cause too much current and blow a fuse, which is kind of like, hey, every time it gets icy, I blow the fuse. They won't use a fuse, they'd use a circuit breaker, and they may have it be a PTC, a self-resetting circuit breaker. So you go to run your wipers and your mirrors and your windows and stuff, and they don't work. But then you drive the car and it thaws, all of a sudden, you know, it'll reset the circuit breaker and they'll start to work again. Same with seats. Like if you get a bunch of junk stuck up under the seat, it'll be hard for the seat to move. If it's too hard for the seat to move, that would blow a fuse. So they don't use a fuse, they'll use a circuit breaker. And the seat won't work for a bit, and then you'll clear the 7 water bottles, 7 of them, from underneath, all 7 of them from under the seat. And then all of a sudden it'll be like, oh yeah, now my seat started working. So they do circuit breakers on things where they expect it may have an overcurrent where it would blow a fuse, but they don't necessarily want you to have to bring it in for service. Kind of makes sense. Right, and so there's some more examples. The colors, you don't have to memorize the colors, but probably eventually you will. So like these would be less common. I rarely see 2 or 3 or 4 amps. 5 is a little more common. 7.5 sort of common. These are very common. Red is a 10, blue is a 15, yellow is a 20. Clear, sometimes we see green, sometimes we see, but like let's focus in on, let's say red and blue. If it's a red fuse, it's 10 amps. If it blows, you don't upgrade it to blue. Makes sense? You no longer are protecting the circuit if you put a 15 amp fuse in a circuit that was designed for 10 and it only has wiring that'll handle 12, right? So that's why we color code them. We don't want people to be like getting confused. So if it had a red fuse, you put a red fuse in it. That's why a lot of times I won't even look at the number. They're color coded. They're consistent. And same if it's the larger fuses. They're slightly different colors though. So for example, red is not a 10 amp. Red is a 50, just so you know. There's some logic. Now, if that made sense, I want to make sure that you understand exactly why we have those fuses. Here's a wiring chart. So if we had a wire size, and we'll get into this when we do wire repair, okay? Because we are going to spend some time on wire repair. If you had, this one might be fairly close. If you had a wire size of, this one's probably actually a little bit bigger, 18 gauge. That sounds really good, right? 18 gauge. 18 gauge is showing you the cross-section area, right? So let's just go with, it's got 0.8 square millimeters. That's actually going to be good for 20 amps if it's outside, 17 if it's inside. And a lot of times this has to do with temperature. So if it's inside something, like if it's in conduit or if it's under carpet or something, they know it can tend to get a little hotter. Whereas if it's outside, it tends to be a little more cool. Now with understanding that, maybe we'll just mostly focus on the outside. The 18 gauge is good for 20 amps. Okay, and given that's with 105 degree insulation. So this is going to be a little generic. Sometimes it depends on the temperature, sometimes it depends on the insulation. And this is with copper, and so if it's aluminum, it's a little bit different. And so don't use this as a direct quote because there's other factors, right? But overall, I want you to understand, if you have an 18 gauge wire, in this example, it's good for 20 amps, which would mean we shouldn't run a 20 amp fuse because it's good for a maximum of 20 amps. So we're probably going to run like a 15 amp fuse. Make sense? And if you had, let's say, a whole bunch of lights on there and you wanted to add more lights, and when you added more lights, now it's starting to draw like 18 amps, that's going to blow your 15 amp fuse. When it blows your 15 amp fuse, you could put another 15 amp fuse, it'll blow that one. Then you could say, oh, let me upgrade that thing to, do you guys remember what the size of the 20 was? I think it's yellow. You could be like, is it yellow or maybe it's, let's see. Let's see if my memory's good. Yeah, 20 amp. You're like, let me upgrade the blue fuse to a yellow fuse. No, because now if you draw 20 amps, that's at the limit of what that wire can handle. That's when this wire can get so hot, it can catch the insulation on fire and burn. So if you added enough lights where now you need to pull more than 20 amps, you can't simply throw a bigger fuse in. How could you get it so that you could draw 25 amps with those lights? Look down. This can do a maximum of 20. If you want 25, you'd have to use this wire size, a 16. 16, doesn't that sound smaller? You had an 18. It's the other way. If it's 18 gauge, 16 is bigger, 14 is bigger, 12 is bigger, right? So the higher the gauge number, if you look, that had 0.8 square millimeters. 16 has 1 square millimeters. 14 has 2 square millimeters. Make sense? So the lower the gauge size, the larger the actual wire conductor size. Okay, make sense? The way that we do this is we say, how many amps do we need to draw? And let's say you said you wanted to draw 25 amps. I probably would not advise going with a 16 because then you're at the literal limit and you're borderline catching on fire. So what the engineers are going to do, they're going to be like, oh, if you want to pull 25 amps, let's bump it up to a 14 gauge and let's put a 25 amp fuse in there with a 14 gauge wire. Kind of makes sense? So if you need to draw more amps, you'd have to get rid of this 18 and you have to go with maybe a 14. You notice this one's a little bit bigger. Makes sense? So when you see a fuse, the reason that the fuse is in there is really because the wire size, what the wire can handle. So if you follow that logic, then why not say, you know what? 14 gauge is better than 18. Let's just run 14 for everything. Why would that not make sense? Think of it as a business. Well, the 14 gauge wire would be an upgrade because you could run potentially up to 35 amps. Even if you only need 25, maybe rather than going to the 18, you just bump it up to a 14, right? So rather than a small wire, you run a big wire. That wouldn't hurt the electrically, that would make sense, but financially it wouldn't. How come? Which do you think is more money? Exactly. Which do you think weighs more? Which do you think takes up more space in that wire, in that harness? So you got to understand, when the vehicle's made, they don't just put in bigger wire just because. Now, if it were me, the way when I did my construction, I built my shop, it was like, well, I only need 30 amps right there, but you know what I'm going to do? Run a wire that'll handle 50 amps. Why? Because I don't know what I'm going to do in the future, and I'm okay with spending the budget on that, but also a house or a shop, it doesn't have to move and drive and get gas mileage, right? So for me personally, I ran oversized wire all over the place just because if I want to add to the circuit or if I want to run bigger things, I don't want the breaker tripping. So, but from a manufacturer standpoint, keep in mind, every time you run a wire size bigger than it needs to be, you're running the budget up. Now you're running a heavier wire, a more expensive wire. If you have a whole bunch of bigger wires in the car, you know a typical car has several miles worth of wire in that vehicle. If you add all the wires up and you do end to end to end, it's like a couple miles. If it's a couple miles of this versus a couple miles of this, you're talking hundreds of pounds differences. Make sense? So they don't want to run overly large wires just in case. They want to run the smallest wire they can and then protect it with a fuse so that wire can never get too hot and burn. And that just makes business sense. It makes the car a little more affordable, or it keeps their profit margin pretty nice. And it also makes it so that it's not going to get bad gas mileage and increased emissions. I mean, it sounds ridiculous, but all that matters. People want a cheap car, and the government requires that it has good fuel economy and low emissions by federal mandate. CAFE, Corporate Average Fuel Economy, and then EPA, Environmental Protection Agency. So the manufacturers are not just running big wire size. Okay, make sense? So if you got a 10 amp fuse that's blowing, you can't put a 15 in there. I guarantee you from the factory, that wire harness is not made for 15 amps. If it is, why would they waste the money? They make hundreds of thousands of that vehicle. They wouldn't put too big of a wire times hundreds of thousands. That's hundreds of thousands of dollars. Make sense? Go ahead.
That wire size of 172 is like breaking the rules. I mean, usually it goes lower, be bigger.
Oh yeah, look at that.
172 and there's 260 amps, or no.
Oh, that's supposed to be a 2 gauge. I didn't actually catch that. I cut this out of something and I pasted it, and I didn't realize that should just be. It should be 64210. I don't know why 172, not 17.2. just 2. And then an interesting thing, 0 has 50 square millimeters, but then what the heck is that? We'll call that like, if you ever talk with an electrician and they're like, oh, that's got 2-aught. And you're like, 2-aught? It's not 2. 2 would be here. 2-aught is like, it's like 0, 0. And then this is like 0, 0, 0. And this is like 0, 0, 0, 0. So as it gets larger and larger, it doesn't start to go back up the other way. It's 0, 2-aught, 3-aught, 4-aught. And I don't really know exactly why they call it aught. It's just the way it is. So if you ever hear somebody say, like when I ran the main power supply to my construction, I did 4-aught wiring. It was so heavy, you can't believe it. Like it was, even one spool of that, I couldn't even pick it up out of my truck. So like when you're talking about wire like that, and then you got to run 3 of them plus a ground, by the time I went to try to drag it, I couldn't move it. I actually had to use an excavator and hook a bucket under it and wrap it and strap it and then lift the bucket up to pull that wire through. Like that, this wiring gets kind of ridiculous. However, if you make some bad decisions in your life and you need some quick money and you go on where they're building one of these new developments, if you can rip some of that wire out of the ground, this has so much copper in it, it's worth cash. You also will go to jail. And if it's live, you die. That's what happens with that. But just so you know, that's why you got these people that may or may not be playing around with certain substances trying to steal this type of wire, because you're talking about 103 square millimeters of a cross section, and they'll pull hundreds of feet out of the ground, and it'll be thousands of pounds, and somehow they get superhuman strength and get it out and get it in a truck, and then they get it to the scrapyard, and they're like, wow, all this copper, here's your $1,000, and then that copper gets melted down and sold for scrap. And then, of course, the construction builders come back and they're like, what the heck? Like, it took us a week to pull that wire, and overnight they stole it all. They're like, we're going to find them and offer them a job. You know, these types of things. It's hard to pull that. So that's just your ampacity chart. And again, you know, I jumped on Google real quick and I pulled one. Some of those numbers didn't make total sense to me. So it depends on exactly what you're getting. So if any of you are going to be like custom electrical engineers, you a lot of times there will be an ampacity chart for the specific wire you buy that has a specific type of insulation and these other little details, right? So that one, use that one as a reference point. It was true for whatever I looked up when I Googled that, but it does vary. Cool. And so now I think you guys kind of understand the breakers. This is the type that I was saying, that it can self-resetting circuit breakers, which are really nice. Here's a shot of a fusible link. You can barely see it, but it's almost like you can tell there's a red wire here, and then it goes into this gummy section that looks like it's heat shrink. And then all of a sudden we're back to regular wire. This would be the section of fusible link. And then that resetting circuit breaker, this is a shot of that. You can see it's two pieces of metal. And when they get hot, it'll separate. You notice there's an open contact now. No power for your windows or whatever. But then when it cools, it actually relaxes back down and touches. Now your windows work. And it'll just reset itself. It's pretty nice.
You can pull the fusible link while it's still on there to see if it's...
Yes, that's exactly what I would do. Like that. If it burned up the copper inside, it'll just be like again, these things come to me, but there was a I don't know if you guys ever decide you want to go out and zoom around the canyons for fun, but at one point I was zooming around the canyon, perfectly legal, but don't do anything stupid, because I saw a kid in a Camaro try to pass 5 cars oncoming on Ortega and slam this Tahoe. And so, unfortunately, you know, nobody could get to it because the traffic all jammed up. And so when I snuck around and I got to him, and I actually broke the windows out of the Tahoe, and I was trying to get the guy out of there, when I grabbed his leg, it felt like a blown fusible link. Like I pulled it, and it was like, oh, it's not supposed to be Gumby. And I'm like, all right, leave them because you don't want to like tear an artery or something. Just reminds me of that. You'll go to grab it and it'll be like, oh, there's no bone in there, right? There's no copper in there. It'll just be kind of gummy. True story. But you'll remember that, won't you? All right. I remember it too. So yeah, that'd be a quick, easy way to test it. You can see electrically it's hard to test it because there's no exposed wire. What I don't want you to do is make a nick right here. Like, don't cut the insulation off so that you can test it, because now you just sacrifice the integrity of the insulation. Makes sense? So it's better to actually tug on it. That's a good way to test those. Okay, and that's kind of what it was saying. Like this right here is a form of a PTC circuit breaker. So that's what it means, positive temperature coefficient. But these can be more like a solid state. Cool. So you can have the bimetallic spring that's mechanical. Those actually make sounds. You can actually hear them heat up and cool down. But if it's a PTC, that's more when we get into the electronics. And those, depending on temperature, will either have high resistance. If it gets too hot, it'll have high resistance. That'll be like an open. And then when it cools down, all of a sudden, boom, it'll close and it'll have continuity and the part will work again. I bring these up because they can be very small and we can simply like have them inside of a motor, right? So if you think you had a problem with a PTC circuit breaker, you'd be looking all over for it. Sometimes they'll actually build it into the component. You'll never find it because the electrical engineers design it inside the motor. The PTC can be very tiny, but pretty fun. And again, they reset themselves typically once power is removed. So if it's that power window, you're trying to run it, it won't work. You just have to let go of the switch and just walk away. That removes the power from it when you stop messing with the switch, and it'll reset. Cool, so pretty good. And then one of my least favorite things, this right here is a fuse. I'll call it like a multi-fuse. Remember how I was saying they're running out of room for all these. So this could be actually like 10 fuses in one. On the end, it'll plug into like a big 12-volt bus, and then it'll go through a whole bunch of fuses to power a bunch of different things. And so if this powers 10 things, and let's just say one of the fuses blow, you got to replace this whole entire assembly. So I don't personally like them for a couple reasons. One, you can't just grab it and pull it out. A lot of times you have to disassemble this fuse box and undo bolts, and it's actually bolted in several spots. And so doing the work is not really fun. And the other thing is you can't stock these. Like, this is unique to this particular application. So the most common time you're going to see something like this is, you know, maybe one of these is for the alternator and one of them's for some other power supply, some other one. If you, or let's say more realistically, a salesperson or the customer jumps their car backwards, you know, red on black, black on red, not the way it's supposed to be jumped. A lot of times it'll blow the alternator fuse part of this, and you'll bring it in, you'll diagnose it, you'll be like, oh yeah, the alternator fuse is blown. You can't really test these because it's all buried, but if you look from the side and you shine your light in there, you'll see the alternator fuse part will be blown. At that point, you have to order this, and that's why this actually has a part number on it, 82620-48140. You have to actually order this, and they can be like $20. They're not super expensive, but I would just love it if it was one of these where I could just yank the fuse out, put in new fuses, and be done. You know, so these kind of irritate me. But they're more and more common because we're running out of space in these fuse boxes because we keep adding more and more electrical components. So for example, back in the day, power steering worked on hydraulic fluid. And it was, right? And then they're like, no, that's not as efficient. It's kind of nastier. Let's do electronic power steering. Now you have at least one or two fuses in the fuse box that never used to be there. And it's the same. Mechanical fuel pumps had no fuse. Electronic fuel pumps have a fuse. Now, back in the day, remember how you put the windows down? Like this. And you put them up like this, right? Nope, get rid of that. power windows, power locks, power this, power that, power the other thing. Less and less room in here. Now we're resorting to things like this. So I understand why. It just irritates me, that's all. Okay? It just does. Cool. So that's it for fuses. Fuses, relays, just general circuit protection devices. Not a big deal. It rolls fairly well into flashers. So when you guys turn on your turn signal, you notice it goes, oh, you don't use turn signals. No, you don't, do you? You just like, I'm keep them guessing. Change lanes. Yeah. Motorcyclists, we appreciate that because we periodically get run over, and that feels amazing. Thank you. But let's just say, I know you use your turn signals. I know you would never do such a thing. So turn signals, you click it down, and it goes. You're actually physically hearing this. This metallic strip, heating and cooling. That's how the old cars would work, right? It would send current, it would heat up, and that would separate it, and then it would not send current. Cool down, click, send current, heat up, open up, not send current, right? So there was actually a mechanical flasher that would heat and cool. So if it's an old school car, you can actually probably still visualize, or you can still probably hear it in your mind, the actual ticking sound. It was that. New car, we don't do it like that. We're going to do it more of like a solid state. It's going to be, it's really going to be an electronic flasher. We can even use the control module to do it. And so we'll just put it on a timer circuit, and that solid state flasher no longer has to heat up and cool down. It just says on, off, on, off. But you lost the sound. So it's kind of a bummer when you lose the sound. So on a lot of vehicles, they'll actually add the sound back in. They have a little mini speaker, something that replicates the sound, because people were so used to hearing the ticking of the old school mechanical flasher that when they went to electronic, they lost that. Or you ever notice, you probably know your own cars, if they're 10 years old, they don't have a mechanical flasher anymore, I can assure you. It may make noise or it may not make noise. Like Fords, for example, have the most obnoxious, in my opinion. It's like it's louder than it even used to be. Like, chill on that. There's no reason for it to be that loud. But on other cars, you turn the turn signal on, it won't make any noise. There is no noise. But if you leave it on too long, now people are confused. That's why some manufacturers will have it make noise, but other manufacturers, if you leave it on too long, it'll just give you a little chime and be like, hey, your turn signal's on. Your turn signal's still on. It's up to them, right? It's up to what the manufacturer decides. Replicate this clicky sound, or give it a new sound, or give a little chime or a little warning or a little something, right? So they were like this, all mechanical, and they had an interesting way of functioning. So if you had a bulb that blew, that would actually change the amount of current going through the flasher, and it would flash fast. So you ever notice that? You got a car, you jump in, you put your right turn signal on, you put your left turn signal on. It's like the hyper flashing, it flashes fast. Right off the bat, that should tell you, oh, I got a bulb out. I don't know if it's the front, I don't know if it's the rear. It could even be the one that's in the mirror sometimes. But if it flashes fast, that's when you get out and you look and be like, oh, yep, the rear turn signal doesn't work, right? So that wasn't on purpose. That was just the nature of this flasher. And if you go way back in the day, we used to like to put LEDs and stuff. And if you put LEDs in a vehicle with a mechanical flasher, it would flash fast all the time. And then we'd have to get a heavy duty flasher. We'd have to add resistors in, and we'd have to do some customization stuff. So these were designed with a certain amount of resistance in mind between the front bulb and the rear bulb. And if you had an open bulb, that would affect the resistance and it would flash too fast. That was the dead giveaway. So old school drivers would know, oh yeah, it's flashing fast, I got a turn signal out. That was your clue. Then when they went to the more mechanical, the electronic type, these actually don't necessarily have to flash fast if you have a bulb out. But for safety purposes, because we want people to know if their turn signal's not working in the back, so that way it's safer for other cars and for themselves. A lot of times what they'll actually do, they'll program the body control module to purposely make it flash fast if it senses a bulb is out. That's not natural. That was natural with this type. That's not natural with the newer type. So even on a newer car, if you jump in and you turn the left turn signal on, it flashes fast. It's because the body control module is checking how much resistance is in each of the bulbs or monitoring voltage drop, and it knows the bulb is out. So a lot of the cars will make it flash fast artificially just to prompt you to get it fixed. Some cars will actually give you a warning light saying, hey, you have a bulb out, and it might flash normally. It's kind of interesting. Cool, so that's the history of the flashers. If you were to look for those, you'd have to actually look up the wiring diagram specifically to determine what type it is. But a lot of them are just electronically controlled by the module now. Okay, so relays. Okay, on flashers. Flashers is like a mini little subject. Relays, we talked about. So if we tie what we learned earlier, I want you to notice this is the coil of the relay. This is what we consider the control side, right? So 85 and 86. Now, I'm okay if you don't want to memorize these numbers. I actually don't really memorize these numbers. For whatever reason, on the domestics, these numbers were consistent all the time. So it was helpful for some technicians to know the numbers. That way, when you went to diagnose the system, you could really quickly know, like, am I testing 85 or 86? 85 and 86 is the control side. But then if you look, 87 and 30, that's more like the high current side. So if we were to trace this out, big battery power comes down and it lands on 30, right? So the source of the power comes in on 30. And then it's going to try to go through the switch and it's going to try to leave on 87. So you'd basically take the thing, maybe this is the thing, whatever the thing you want to power is, and you'd send 87 to the thing, right? So if there's power on 87, the thing goes vroom vroom or turns on or whatever. Does that make sense? So 87 goes to the load you're trying to control, okay? However, how do we control 30 and 87? If you have no magnetism here, 30 and 87 are open. So you get no power on the thing. But if you also look, big power comes in and it goes to 30, but it also splits and goes to 86. So if 86 gets voltage all the time, how could we magnetize this? We would give ground on 85, and that's why we have a little switch right there. Now this little switch could be in the ECM, which means it's probably a transistor. Or it could be the horn switch. So when you as the driver press the horn switch, you're actually closing this switch, which is giving ground to 85. It already had 12 volts on 86. So if you have 12 volts on 86 and ground on 85, doesn't this become magnetized? Right? You have current flow. This is the load of the control side. It doesn't make light, but it makes magnetism when it gets 12 volts in ground. If it gets 12 volts in ground, it becomes magnetized. Can you see what it's going to do to the switch? Boom, pull it closed, which means 12 volts is going to go out 87 and power the thing. The horn, the fuel pump, the starter motor, whatever it is. Kind of make sense? Now you can visualize this relay a little bit more specifically with the diagrams. Now part of this point is we put a little diode right here because when you're magnetizing and unmagnetizing, sometimes it can make a little voltage spike. This allows for the current to basically drain back. Make sense? It prevents a spike, but also it makes sure that you could figure it like this more simply. Electrons don't get kind of like trapped in there. This allows the electrons to leave. If you open up this ground, the electrons can't make their way back there, so it'll make like a a little drain, but it'll make it so it doesn't kick back and, spike the ECM. This is especially important once we go to computer control. Cool? Okay, go ahead. The diode's DC, and this is powered by DC, but what's interesting is when we open and close when we build and collapse magnetic fields, it can induce a voltage, and it could be AC, it could be DC, but we could unintentionally induce a high voltage, and so the diode is going to prevent that from going back to like an ECM. It's basically its main function. So if you were to have a relay that has a diode in it, that's most likely to protect the electronics, and then let's say you were to yank that one out and put one without a diode in there, you may be putting some of those electronics at risk, which is part of the reason you will see me swap relays sometimes, but I'm going to swap one relay for the same relay. So if I pop a fuse box off and I see part numbers on relays, if it's the same part number, they're all the same. But I won't grab a relay from over there and put it over here because I don't know, maybe it doesn't have a diode and maybe it's supposed to have a diode or something. So it's more just something to log in the back of your mind that some of these relays have diodes inside to protect the spike of the electronics. Protect the electronics from a spike unintentionally. Cool? Feel okay? The main part of the relay is just knowing power comes in, can't go through here because it's normally open. But if we want to close it, we just give ground on 85. That will magnetize this, pull it closed, and now we'll have 12 volts go through and go down 87 and power the thing. If you were to look at it in a wiring diagram, it would look like this. Now you notice those relay numbers are gone, right? Here was generic domestic relay numbers. Here, not so much. This is Japanese, but these are not necessarily consistent in all manufacturers. So if we were to look at this, you'd say, oh, main power supply for the fog lamps goes through the fuse. That's why it's a 15 amp fog fuse. Goes to, in this case, terminal 5, and that's it. It stops. You know why? Because it's normally open. If we want to power the fog lamps, go to the load, what would we have to do to make 12 volts go through? Right now it stops at 5. What do we need to make 12 volts? What do we need to do to make 12 volts go through to 3? True, yeah. So if we were to look at this, this is a little vague. It's saying we have 12 volts coming in, going to 1. And then if we look, 2 goes out and it goes to the ground. Now where's the switch? In this example, I didn't give it. We could have a switch on the 12 volt side. And yes, if we close the switch, now 12 volts hits the coil, which would mean ground it would have all the time, right? Or we could have 12 volts all the time and we could have the switch on the ground side. The switch can give 12 volts or the switch can give ground. If it gives 12 volts, that means this has ground all the time. If it gives ground, that means it has 12 volts all the time. In this case, I didn't give you that information. But what you're correct about is if we get 12 volts on 1 and ground on 2, this will become magnetized. This will pull the relay contacts over. Now your 12 volts will go through and go power the thing. The fog lights in this case, the load. Okay, make sense? But wait, there's more. On this diagram, what you can see are these numbers, but you'll notice this is all inside of a gray box. You may not actually be able to test points 1, 5, 3, and 2. You may need to test outside of the box, which is here. Like you see this red wire? There's a number 10 right there. That's connector 2C terminal 10. So I'm giving you the fundamentals of how the relay works, but to get a real complete understanding, you got to know how to read a wiring diagram. So if I wanted to test terminal 1, I can't. It's inside the box. I would need to test terminal number 10, which is in the connector like we were talking before. Terminal 10 may come in like this, and you actually have to locate number 10. What color do you think that's going to be? Red, yeah. So I could find terminal 10 and be like, hey, do I have 12 volts there? The reason this one's kind of weird is you can't exactly test this, but you can test at the top of the fuse, and the top of the fuse is going to go right to 5. Then you could test the ground at terminal 4, which happens to be red with a yellow stripe. And then you could test the load, which happens to be terminal 12. So let's say it was back to that fuel pump example. I want to know, is the fuel pump good or bad? I need to see, does the fuel pump have voltage or not? If the fuel pump's not running, I may very well go, let's say if I go to the fuel pump down here and it has no voltage, I'd be like, oh, it's not getting voltage, let me backtrack. I may go to terminal 12. And when I turn the vehicle on, that means that this should magnetize. That means that I should get 12 volts right here at terminal 12. If I don't, I know the problem's up here. If I got 12 volts right here, but it doesn't make it to the pump, I would know that it's in the wire. But let's say that I have 12 volts at the pump and it still doesn't work. Assuming the ground is good, I know it's the pump, right? So we're building this understanding again to the point where you can actually diagnose why the thing doesn't work, whatever the thing is. In this case, we talk about the pump, but really it was the fog lamps, right? If the fog lamps don't work, it could have 2 bad fog lamp bulbs, but probably not. So you'd probably do a lot of your troubleshooting right here at the relay. And if you wanted to be really down and dirty, one of the things I would do is I would actually just put my hand on the relay and have somebody turn the fog lamp switch on and off. And do you know what I'd be feeling for? Heat's one thing, but I want something a little more audible. I want to hear or feel the click. If I hear or feel the click, that's this little contactor moving over. Click, click, click. If this is clicking, I could tell a lot about that circuit, and I never even measured one thing. If this is clicking, that tells me terminal 10 is getting 12 volts and terminal 4 is getting ground, because that's what it takes to magnetize it to give me the click, right? So that's why it's helpful to really know like the whole theory, the whole thing. You can do quick diagnosis if you understand it. All right, and then you guys know we talked about relays a little. Normally open, a normally closed, and then of course we get double throw relays, which would be like if it's magnetized, it contacts 5 and 3, but if it's not magnetized, it contacts 4 and 3. Those are helpful in a couple ways. One, sometimes we'll just call them a feedback relay, where the computer will actually monitor, the ECU may monitor, is there continuity between 4 and 3, in which case the relay's closed. Or if there's no continuity between 4 and 3, that means, if there's continuity between 4 and 3, that means the relay's open because they're contacting here. If there's no continuity between 4 and 3, that would mean the relay has moved over and must be touching 5, right? So sometimes we'll add 4 over there as a way to monitor the status of the relay, because the ECU may want to know that for one reason or another. And other times we'll make it so this maybe 4 powers, maybe 4 being going to ground does something, and then if we take ground away from 4, maybe that does something else. So we could do 2 things with these relays. But most of the time, it's for like ECM to monitor, to know what the status of the relay is. Okay, and then what the heck is this? Solid state relay just means there's no actual moving parts. That's we're going to use that NPN or PNP junction to make continuity or not. More than likely, this is actually going to be a transistor. But sometimes transistors confuse techs, even seasoned, current professional technicians that are making double minimum wage still can be a little thrown off by transistors. So instead, they may draw it as a solid state relay. They may even give you all these same numbers. So that way the technician could measure it like it's a relay, but there is no relay. The relay doesn't exist. It's probably a transistor, and they just redo the diagram so that the techs can diagnose it better. Kind of crazy. The negative to that is if there's no physical relay and it's a solid state relay, which means it's really a transistor, you can't replace it, right? So back in the day, techs would be like, oh, I know how to diagnose a relay. I rip the relay out and I switch it with another one, and if it fixes it, it fixes it. And that's actually true, and there's nothing wrong with doing shortcuts like that. But if it's a solid state relay and it's built into the module and it's really a transistor, you can't rip that out and sub a new one in there. There's no swaptronics. All that's gone, which is further justification for why you really need to know this stuff. And you really need to be able to actually diagnose it. You can't just be swapping things. Swapping is less and less practical or even possible. Cool. So that's all a solid state relay is. It's really a transistor. Overall, probably pretty good on relays, I'd say. I don't think there's anything else that I absolutely need to discuss. Just understand the small current controls the big currents, right? So like over here, this side right here, I call the control side. That's small current. You may need under an amp, a quarter of an amp, just to give a magnetic field right here. Whereas this may control up to 15 amps. You kind of get the purpose of the relay, right? Small current controls big current. Small wires are easier to have go through switches and modules and stuff. Big wires go directly to the load from the power supply. Cool. Well, it's probably good on relays, I think. Well, almost good. Did you know relays can fail in several ways? So let's say we start with this one. What do you think would happen if I had an open right here in that magnetic coil? The picture like a light bulb, right? You see the filament in the bulb? If the filament's blown, what happens to the bulb? It doesn't work. Yeah, that's right. So it doesn't give us any light. What do you think happens if this coil is blown open just like the filament? Bingo. Bingo. So you'll go to turn the relay on and off, the relay won't click, the thing won't work. The fog lights don't work or whatever. The fog light's not working could be the relay. How would you test it? Well, you could be like, oh, let me make sure I've got 12 volts here. Let me make sure I've got ground here. And if you have 12 volts and ground here, you should be hearing you should be hearing a click, right? And if it's not clicking, I would suspect you may have an open coil. But there's another good test you can do. You can take your meter and put it on ohms and measure from 1 to 2, and you should get like, I don't know, some number, maybe 100 ohms, maybe 1,000 ohms, maybe 10,000 ohms. You know what you should not get? OL. If you have OL right here, that means this magnetic relay coil is open. So they can fail on the magnetic coil side, yes. And that to me, that's a quick diagnosis because remember, I'll grab the relay and I'll be listening and I'll have somebody turn the switch on and off. I'm listening for it to click. If it doesn't click, I'm trying to diagnose over here. Now it may not click because it's not getting 12 volts or it's not getting ground. So we still have to make some measurements. But if it does click, that doesn't necessarily mean it's good. That just means it's magnetizing and this contactor is moving. What do you think would happen if I had a bunch of corrosion right here on terminal 5? True, so let's say it had corrosion. We could have 12 volts coming down and now we have a bunch of unwanted resistance. You may only get 6 volts going out and that fuel pump may not work very strong. Or those fog lights could be really dim, right? So you could have excessive resistance in the contactor. Or let's say that you had a lot of resistance. You might have 12 volts coming in and basically 0 volts coming out, and the fog lights won't work at all. And that could be, corrosion on the relay contacts or a bad connection on the relay contacts. The fix would be a new relay, by the way. And because that relay is opening and closing, there's always the chance that the relay actually welds itself closed. So if the relay arcs and arcs and arcs and does a little weld, now 5 is permanently connected to 3, what's the customer's concern? Yeah, the fog lights won't shut off and it kills the battery. And you hook the battery up and you're like, the fog lights are on. And you're like, oh, something's shorted. Well, yeah, that could be true, but the relay actually could be welded closed. So you actually could just pull the relay, and if the fog lights go off, then you put the relay back in and they go on and on, off and on. And you'd be like, oh, this relay is unable to open. This relay is welded closed. That happens too. I've seen that a few times with cooling fans. Cooling fan relays will weld themselves shut and the cooling fan will just run and run and run and kill the battery. It's for some reason common on some Hondas. Cool, so that's the failures of relays. I think totally solid. And this is just, giving you more diagrams. They can look different ways. It's all relay stuff. Cool. This one I think you're good. This was just showing you the rest of the fog light diagram, right? 12 volts went to the relay, but 12 volts doesn't go through the relay to the fog lights unless we magnetize this. How do we magnetize it? Well, it's got 12 volts all the time, so what do we need to give this coil to make it magnetized? Ground. So we have ground. The switch either interrupts the ground, which won't magnetize it, or if the switch closes, it'll send the ground, which will magnetize it, and boom, the fog lights will come on. Or the headlights, or the horn, or the fuel pump, like so, right? So applying it to more of a fuel pump, you'll notice this is going to be very similar. Battery, 12 volts goes to the fuse. 12 volts goes down here to the relay, splits off. We've got 12 volts going to the coil side. That means this side would be ground, right? So if 12 volts is here, this would have to give ground. Can you tell what's going to control the ground on this side? I don't see a switch there. Do you? But what I do see is I see the PCM gets ground and ground goes into the PCM, and then it's a mystery. But if I look at the diagram, we can all agree this top side of the coil has 12 volts, right? Which means how we must control it is we must give ground or not give ground. Who can do that? The PCM can do that. The PCM is going to use a transistor in here to do that. But guess what? It doesn't show a transistor. Why? I don't exactly know. The engineers are like, you don't really need to know what's going on in there. That's our work. That's a secret thing. And we're like, yeah, but we need to fix it. So how are we supposed to fix it if we don't know what's going on? It would be implied to you that if it has 12 volts all the time, it must give or take away ground. And if it goes into the PCM, PCMs have transistors in there. You would just have to, by default, know. The PCM uses a transistor to give ground or not give ground. Cool? So if the PCM gives ground, that's going to magnetize this, right? What should happen? Close the contactor. Now 12 volts will make it to this. What the heck is this thing? An M. Oh, that's a motor. That's our fuel pump right there. What controls the fuel pump? Well, technically the relay controls it, but what controls the relay? The PCM controls the relay, right? The PCM, anybody know what that is?
Power.
Yeah, powertrain control module. So the computer that runs the engine, logically, will have the say whether the fuel pump runs or not, right? So this is just very specific application to how the relay is controlled by the PCM, and ultimately how the PCM controls the relay to control the fuel pump. So if a vehicle has a crank no start and you say, hey, the fuel pump doesn't run, that's why we can't just say, hey, chuck a fuel pump in that bad boy. Yeah, the fuel pump doesn't work, but it could be the bad pump, it could be a bad ground, it could be a bad positive, it could be a bad relay, it could be a blown fuse, it could be an open at the PCM. It could be the PCM itself, right? So when the customer comes in and they say, my car won't start, we're getting them to authorize diagnosis time because we got to go through and test all this stuff to see, like, maybe it's the pump, maybe it's the relay, maybe it's the fuse, maybe it's the wires, maybe it's the PCM, maybe it's the ground of the PCM, right? We don't know. We don't know. No technician is that good. Trust me. because it's not really a matter of good, right? Like you guys have seen Caesar Milan when they got the dogs and the dogs are misbehaving. He kind of comes in and like he's the dog whisperer. He kind of like talks to the dog and he's like, "Oh, I know what's wrong with your dog." I'm pretty sure that's just a TV show. With cars, nobody can walk up to the car and be like, "Tell me, baby, what's wrong? Why won't you start?" "Oh, it's an open between the PCM and the relay? Thank you. Thanks for letting me know." Like, no, it doesn't work that way. You have to understand it could be all these things. Then we got test and test and test. How do we test? Well, maybe we test like this. If you want to know if 12 volts is coming through the relay, you can measure available voltage. You can put your black lead on a ground and you can put your red lead on the output of the relay, right? So that would be like the equivalent of measuring right here. And you'd be like, are you giving power or not, right? Or maybe it's the equivalent of measuring right here at the motor. So we're going to spend a ton of time doing these tests and how to do the tests and how to measure the available voltage and what the voltage should be and stuff. But like, you got to have a good understanding of how these components work first, and that's why we cover this first. So this is just one test to determine whether or not the relay is working. And we may have to test over here, we may have to test over here, we may have to test over here, we may have to test up here, we may have to test down here, we have to test all over the place. But then by the time we're done, you could say like, this is what's wrong, right? So if you go to the doctor and you're like, "Oh, I have a tummy ache," and they're like, "Oh yeah, that's because you ate this bad food and you need to, your gut is a biome and all the health concerns come from your gut," and you'd be like, "This doctor's freaking me out. They did no testing, they didn't even check anything, and they're automatically telling me what's wrong." Like, that's not right, right? So when you go to the doctor and they do these tests, like I told you, I was sick a couple weeks ago. I actually requested myself, like, "Can you do chest x-rays? I want to know what I got going on in the lungs." And they look and they're like, "Oh yeah, stuff looks good in there." How do they know my lungs are okay? Because they did the chest x-ray. So it's the same with us. You have to perform tests to know if something's good or bad. Make sense?
Is it normal for that powertrain module diagram to look so confusing? Is that?
Yeah. Oh yeah. And that's a big part of, like with electrical, we're going to cover all the components. But then when you get into this would actually be more of an A8 engine performance concept. And you'd be like kind of marrying what you learned in this class versus what you learned in engine performance and be like, well, it's got to work like this. It's kind of irritating, to be honest with you. But from what I've talked with engineers, so as a technician, you don't really get to talk with engineers, but now teaching and going to the manufacturer training and being part of these things and being on curriculum development with the manufacturer, it's like, "Hey, why don't you tell us what's in there?" And they'll be like, "You don't really need to know." And so I asked another, as far up as technicians go, would be like a corporate trainer for the manufacturer. So I asked this guy, and he works for, it's a company, it's a distributorship called Gulf States Toyota. So he's like way up there, like way, way up there. And named Daniel. And I asked him like, "Hey, you ever really ask your engineers?" He gets to talk to the engineers from Japan. Like, you ever really ask your engineers, like, what's their problem? Like, just show us what's in there. And so he told them like, "Hey, you need to tell us, you need to show us." And from what he told me, the engineer said was, "Daniel-san, you think too much. You think too much." And it was like, but what? And so that's it. It's just, I don't know. I don't have really a great answer. They just say like, you don't really need to know the details. And in some fairness, they're kind of right, because if you just know that the PCM gives the ground or it doesn't give the ground, I don't know how it gives it. I'm going to assume it's a transistor. I'm probably right. But this is the point. If the PCM doesn't give the ground, the problem's in the PCM. That's all I need to know. I don't need to necessarily know if it's this transistor or that transistor. All I need to know is I'm selling a PCM because the PCM is not giving the ground it's supposed to give. So I kind of get what he was saying, but I'm still a little irritated by that. It's kind of arrogant, right? And this is just showing like sometimes relays, you can get relays that'll actually have timer delays. So like one of the common ones for this would be turbo timer. You got this cool turbo car and you do some big pulls and it goes zoo, 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 and you make these fun noises. Then you do social media things and people are like, oh, let me follow you because your car goes zoo, 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 and that, you know, whatever. That turbo being all revved up like that is cool, but then when you pull it into at home and you shut it off, it's actually not good. It'd actually be better to keep the car running for like 3 minutes or 5 minutes or 15 minutes, depending on how hard your drive was, and just idle, because the hot oil that's in the turbo is going to circulate down in the engine, and then the engine's going to somewhat cool it with an oil cooler and then send cooler oil to the turbo, which will help cool the bearings down and just gradually let everything cool down. Well, the thing is, you want to get out of the car, right? Like you got home, you want to go inside. They have turbo timers and relays like this where you can turn it off, take the key out, lock the car, walk inside, and this relay may stay active and continue to run the ignition and continue to run the fuel pump for a certain amount of time. And sometimes you can actually adjust the timers on these. So it's not generally factory, but I thought it's a neat thing to show you. That's the idea behind some of these turbo timers. Or I've even seen people add this to like headlights. You know, if you have to park far away from your house and you can't really see, you could turn your headlights off and then it will keep the headlights on for a certain amount of time. You could do this with a time delayed relay, but a lot of times the manufacturers catch on to that and they're like, we don't need a time delayed relay, we'll just write it into the computer to have the headlights stay on for 3 minutes so you can get your butt inside. Makes sense? So there's these concepts. They may start aftermarket, then the manufacturer takes it and says like, yeah, we're going to include that from the factory just by adding programming in the module. Kind of fun. Sometimes you can adjust them mechanically, or in the new stuff, you can adjust them in your settings. How long do you want the lights to stay on? Pretty cool stuff. Okay, new component, solenoids. New, but we've covered it, but we're going to go more in detail. Solenoids, electromechanical. What that means is we send it electricity and it does mechanical work. Makes sense? So if you send it electricity, it uses magnetism and it moves. So, for example, that power door lock. If we have the power door lock rod, the thing you push down to lock and you pull up to unlock, if we put a solenoid around there and we activate it, it has the ability to go thunk. Make sense? That's like the most basic example. So we'll have insulated wire that's wound many times around a hollow cylindrical something, like around the lock rod, but probably more realistically, like if you look at one of these, this is an example of a shift solenoid. This is actually a VVT solenoid, probably an OCV valve. This is an injector, right? We're going to have a winding around a metal object that's going to make it move. When the winding is energized, the resulting magnetic field attracts the mild steel, drawing it into the form and producing a linear motion. That's a lot of words. Let me show it to you how it really works. Here's your injector, right? Your injector's got fuel pressure coming down from the top. You don't want your injector on, so you just don't power it. Fuel pressure will sit right here. But then you got a little electroconnector. If you give it 12 volts in ground, that's like giving 12 volts in ground here. That's going to create a magnetic field, right? And it's going to take this piece of metal and it's going to lift it up. And when it lifts it up, that's going to open up a passage. And now the fuel is going to flow down here and go out this little pintle and spray. And then what happens when you want to turn the injector off? You just take away the 12 volts of the ground. On injectors, a lot of times we ground control them. So we'll send 12 volts all the time and we'll pulse the ground. You give it ground, injector spray. You take ground away, injector no more spray. But we do it fast. The ECM will do it. So imagine in the most simple form, if you were to have it like this, you could connect this to like a switch and you could say, spray, don't spray, spray, don't spray, spray, don't spray. But we want to pulse injectors so quickly that the ECM is probably going to use a transistor. There's that term again. And the ECM is going to say ground, 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 ground. It's just going to pulse the ground. And every time it pulses the ground, it makes that magnetic field. It lifts that pintle and the injector sprays. And then it closes and opens and closes and opens and closes, right? So as a general understanding, if we have 12 volts and ground on this winding, it's going to move this thing. That could be a fuel injector. That could be a transmission shift solenoid. So if we were to temporarily apply this to transmissions, let's say you're in first gear and you want second, the computer can activate the second gear shift solenoid. It'll get 12 volts and ground. It'll move the metal. When it moves the metal, fluid will go, boom, and apply second gear, right? So another example may be, how about, you guys ever notice when you get in the car, it won't shift out of park until you turn the key on and then you press the brake pedal? A lot of times what happens is you're pressing the brake pedal, that's giving voltage to this thing called a BTSI solenoid, a brake transmission interlock solenoid. When it gets 12 volts and ground, it pulls out of the way and now you can move the shifter. If you get in the car and you're very quiet, you can actually hear it. You'll step on the brakes and you hear just like a little slight clunk from the shifter area. That's actually a solenoid dropping out of the way. But if you don't give 12 volts to the solenoid, the shifter won't move. Make sense? So we use solenoids over and over in a similar way. The first example actually was way back here. This is a solenoid. This winding actually pulls this piece of metal over. The relay is like a solenoid. But a relay is kind of like a solenoid and a switch, so we don't usually lump those in. So we could use this concept of if you give 12 volts and you give ground, it'll move metal, and we can send fluid, and we can unlock the shifter, and we can spray fuel, and we can do stuff, other stuff, I guess, whatever stuff you want to do. We can do it. Just understand the way we do it, we have to give 12 volts and ground, and that'll give a current flow, which will generate the magnetic field. We can control it on either side. You can control the 12 volts, or you can control the ground. You can control it with a push button switch, or you could control it with a computer using a transistor, and the transistor gives the 12 volts or doesn't give the 12 volts, or it gives the ground or doesn't give the ground. Okay, kind of makes sense? And so this is just what an injector looks like solid. So the two wires come in here, one is 12 volts and one is ground, and one of them is being pulsed most likely by the PCM. And that's literally why an injector clicks. So down and dirty trick on an injector, if you start the car, you could actually put a little stethoscope on there and listen to hear tick, 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 tick. If you hear the injector ticking, that means the solenoid is magnetizing and it's actually moving the little iron core. If it doesn't tick, 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 you'd be like, let me see if it's getting 12 volts and ground. If it's getting 12 volts and ground, it should move. But if it's not moving, then the winding, there's a problem in the injector. But if it's not getting 12 volts, you look at the diagram and you find out why isn't it getting 12 volts. Or if it's not getting ground, you look at the diagram and you measure and find out why it's not getting ground, right? And that's what we'll be doing for the whole rest of this semester, right? Another crazy example, technically, the horn is a solenoid, although it's kind of a weird example. When you want to beep the horn, it's probably going to go through the switch and the relay and all that, right? But when it gets to the actual horn, we're going to magnetize that, and that's going to actually move the magnetic part. And when it moves the magnetic part, it's actually going to vary this little air gap, and it's kind of weird, but it makes a vibration. So when you hit the horn, depending on, if it's a high note or a low note, it's actually going to make a magnetic field and make a little vibration right here. And the crazy thing is, if it vibrates it kind of slow, that's a deep horn, like a whoop. But if it vibrates it really fast, that's like a high horn, like a beep. And then to make it sound good, a lot of times we use a high one and a low one, and it's more like, oh, that horn sounds healthy. So if you hear a horn that sounds weird, it's probably because the low horn's not working or the high horn's not working. They're both just solenoids. Now, who knows how this mechanical electromagnetic vibration, how does that make sound though? All right, that's where it gets like physics. It's moving this diaphragm, and this diaphragm is pulsing air, which means it's really just a vibration. And if you think about it, all your eardrum is a vibration detector. So if it pulses a diaphragm and that pulses the air, and the air pulses your eardrum, and you're like, oh, someone's beeping the horn at me. Oh, the light's green, time to go. Makes sense? I mean, really, that's what we're doing. 12 volts in ground, make this thing vibrate, and that makes you wake up, get off the phone, and pull through that green light that you were sitting at for no reason. Cool? Okay. That's solenoids. Solenoids are doable, not that crazy. The reason we progress like that is because motors is going to be a little more complex. But I don't want you to be too stressed about it, because like a lot of times we don't totally need to know all the intimate details of how the motor works. We just mostly need to know the motor needs 12 volts and ground to turn, okay? So when we talk about motors, just understand they're going to use magnetic fields to create rotary movement. So we can take 12 volts and ground, generate a magnetic field, and as a result of that magnetic field, make a thing spin. Cool? So like this starter, if we give 12 volts and ground to this, the internal mechanism is going to actually make this start to spin. I'll show you the mechanism. And we could go like totally nuts on motors, but I'm going to reel it back a little bit. Okay? It's going to talk about armatures, which have coils, and sometimes the field can use electromagnetics or permanent magnets. So like on an old school motor, we actually would magnetize this rotating part, and we would magnetize this fixed part. But that's kind of inefficient. It's like excessive. It's like, why would we magnetize both? Why don't we magnetize one electrically and then have the other one just be magnetized all the time? And that's, if you hear the term permanent magnet, it's because generally we'll take one or the other, probably the fixed part, and we'll just put permanent magnets there and be like, hey, you're magnetized all the time. And that way we can only have to control the rotating part. Okay, so that's just the overall. Now, if you were to look at like some examples, how about this is technically a solenoid. This is solenoid. They take the current and they make it magnetic and they make movement, right? But it makes, if you get 12 volts in ground, it'll move it this way. If you get 12 volts in ground, it'll move it this way. What's the difference between a motor then? A motor is going to have a mechanism where it's going to switch over and over and over, right? So with just a solenoid, we only move it one way and then we release it. With a motor, we give it 12 volts in ground, and then a mechanism inside is going to switch 12 volts in ground to ground and 12 volts to 12 volts in ground, and it's going to continue to move it in a rotation, right? So that's kind of the overall, what that looks like. If you were to look at even this, did you know you could make an electromagnet using a battery? If you were to take, like, let's say a paper clip or a coil of wire, touch it to the positive, wind it around a nail a bunch of times, and then touch it to the negative, this will generate a magnetic field which will make the nail magnetic temporarily, and you could pick up paper clips and stuff. But then what do you think would happen if we were to open up either the positive or the ground? It'd no longer be magnetized. So understanding that concept, we can make something have a magnetic draw by giving it 12 volts in ground, and then we can stop it too. And if we switch these two, like let's just say this side became the magnetic side that's going to attract. If we were to actually switch these two, we can make it actually repel. That's where it gets really tricky. And so we're doing that same type of thing in here with a starter motor or with a compressor clutch. So if you look at this, we're going to do 12 volts on this wire, which is going to touch this, like this right here. We won't get into all the details, but this will be a commutator, and that's going to go through, and this coil of wire right here is going to become magnetized because that coil of wire is then going to go through the ground, right? So the positive comes in, goes around, and then comes out and goes to ground. So to make this motor work, we need to give it 12 volts here, and we need to give it ground here. And when we do, it's going to interact. You see, we have a permanent magnet on the left and a permanent magnet on the right. And so I'll give you the basis. When we do that electromagnet of the center part, which let's call that the rotor rotates, okay? It's going to make the rotor magnetic, and let's just say in this case, this becomes a north, and that's going to be repelled away from this north and drawn to this south. Make sense? So you see, this is going to try to turn about 90 degrees because opposites attract, am I right? So if we make this one more like a north, it's going to push away and pull right down to here. Okay, and then once it gets right to there, how could we keep it moving? I'll give you a clue. If this is a south, we can't change this. This is a permanent magnet. But what if we were to make this one the positive and this one the negative? Now this would become the south, and wouldn't it try to repel? So that's what we're going to do. We're going to do positive, negative to attract it to here. Then we're going to do negative, positive to repel it away. And then we're going to switch to positive, negative. And remember that we have two different coils. One of these is going to be being repelled and attracted, and the other one is going to be being attracted and repelled. And so as long as we give the 12 volts in ground and we keep switching the 12 volts in ground, it'll keep trying to attract and repel and attract and repel and attract and repel. Is that kind of crazy? So that's the motor action. The motor action is simply, we make it an electromagnet. If we don't make it magnetized, you know there's no north and south on this rotor part. It has no magnetic draw to the stator, which is the stationary outside. Cool, so how do we make the motor work? We give it 12 volts, we give it ground, and that'll start to spin. Now where it can get a bit confusing is if we give it 12 volts and ground, it's only going to spin part way, then we got to switch it, right? 99% of the time, the switching is going to occur inside the motor because these are going to be weird little segments on a commutator. And this thing right here is going to naturally switch positive and negative. So what we do to the motor itself, externally, we just give it positive and negative. But internally, it's switching the positive and negative all on its own inside because it has a little spinning thing that flips. The flipper, you may say, is right here called the commutator. Now, the reason that I don't cover this in great detail, although it's interesting to me, if you have a bad starter motor or fuel pump motor or windshield washer motor or whatever, what do you think we're going to do? You take it out, put it in the garbage, get a new one, put the new one in. But back in the day, people would actually take this apart and diagnose the details as to why. And you may have a brush right here riding on this commutator. You may have a damaged commutator. Sometimes they have these slip rings because if this is spinning, it's hard. You can't hardwire 12 volts and ground to this. By the time it spins, the wire is going to get all tangled up, right? So it has to have some sort of a way to give 12 volts and ground to a thing that's going to spin. And most of the time that's through like brushes. Back in the day, we would take stuff apart, not we, like the people before me, would take stuff apart and like put new brushes in and clean up the commutator, and there's like slip rings, little contacts and this stuff, and they'd like fix the motor. And now we take it out and we put it in the garbage. Just put it over there. Just go over there. It's garbage. So while I like to explain some of those details, we got to be realistic. You're not going to rebuild those. So I'm going to cut some of the material out. When you go through the textbook, it's going to be pretty intense on what type of motor and how it works and why it works. And like, you got a commutator that does the flipping, right? But then on like newer motors, you'll have an electronic commutator where a transistor is flipping the positive negative. There's no actual connection. Have you heard of brushless? Right? Brushless is like a better thing, you think, right? Because brushes would wear out. The brushes would contact the commutator, which would flip positive and negative, but the brushes would wear out, so it's kind of junky. So they're like, you know what? Let's just eliminate the brushes, and then let's make a little computer flip the positive and negative, because the computer can be so fast, it can electronically commutate the motor, and we no longer have the wear item, which is the brushes, right? So like you could go in depth, or you could go down a rabbit hole on this. But guess what? If it's bad, we're like, oh, is this an electronically commutated? I don't care. Throw it in the garbage. Right there. All you really need to be able to do is tell whether it's getting 12 volts or ground. So if I were to back up, remember this diagram right here? Yeah. We're like, oh, we need to diagnose the fuel pump. Is it getting 12 volts right here? Yes. Is it getting ground right here? Yes. If it gets 12 volts in ground but it doesn't work, it's in here. I don't know if it's the brushes. I don't know if it's a magnetic field segment. I don't know if it's something with a winding on the rotor or a permanent magnet damage on the stator. I don't care. I really just don't. It's like, oh, it's got 12 volts in ground and it doesn't work. That means it's bad. Put it in the garbage. In the garbage. Or maybe they have a core charge. You know what that means? You got to give them the old one. And then they give you the remanufactured one. Do you know what happens to the old one? Somebody does, but it probably ain't happening in the U.S. We're too expensive around here. We'll be like, oh, yeah, I'll rebuild starters all day. I want $20 in a union. And they're like, what? We were planning to pay like 70 cents for the day to do 100 of them. That's going overseas somewhere. Makes sense? So like, yeah, there are places where they still do this work. When I was a kid, actually, if you had a bad starter, you could drop it off at this place, Excel or something, and they would actually rewind it, rebrush it, bushings, bearings, whatever, spray paint it up and give it back to you like that same day, like at the end of the day. You'd be like, oh yeah, I got it. Now they're out of business. Now you roll up to the store and they give you one that's been remanufactured, possibly Mexico, most likely, maybe further south. Not likely to be Canada. Probably not going to be China because it's too expensive to ship it to China. So we're going to send it to like a lower cost country that's closer and have them remanufacture it for us. And by the way, the remanufacturing process that they do may not really be all that good, so I understand some of the arguments of like, we should go back to rebuilding those. That way we have the quality control. But like, if you tell the customer, hey, I'm going to rebuild your starter, it's going to take an hour. Oh, cool. What's your labor rate? $175 an hour through the shop. And they're like, yeah, never mind. We're good. Just throw that one in the garbage. I can get on Amazon, $125. And it'll be here delivered by a drone in 4 hours. Like, there's no business for it. Even though I can kind of relate to, you use a reman motor and it doesn't work and you're like, oh, it's bad. I got to get another reman motor. That does happen. Cool. And that's kind of what this is more saying. Like, if you were to look at it, this has all these magnetic fields. So if you look, the armature, you could say, is kind of like the rotor. Each one of these is going to have a winding. And remember, we can make it positive and negative, which will attract it. But kind of similar to how we were back here, this is just showing you one. So remember how if this one becomes the North Pole, it's going to pull down to here, and then it's going to switch and repel and pull all the way over to here. It's just like that, except imagine that wouldn't have a lot of power, right? The further it gets away, like right here, if this is north, it doesn't have a lot of pull down to this way. It has the most pull as it gets closer, and then it gets weaker, 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 you wouldn't have a lot of smooth consistency and a lot of power if you only had like 2 poles. So they basically take the motor and they do that over and over again. So you'll have a north and a south and a south and a north and a north and a south. And so it doesn't have to pull it 90. It only has to pull it a little bit, and then it's pulling the next one, the next one, the next one, the next one. So this is essentially the same as that more simplified one, but it has a lot more going on. Part of the reason I like to show you this is you could have, let's say, these brushes that are riding on the commutator. Those brushes could wear, and then it won't make contact for positive, negative, and the motor won't work. And sometimes the brushes just get a little stuck. So sometimes what we'll do, this is going to be kind of crude. I'm going to do this gently because I'm not going to be mean. But you could take the motor, if it's a starter, and be like, hey, hold the key to crank. And be like this. Wham, 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 wham. And all of a sudden it'll work. You ever seen that? Oh, yeah. Well, it's a thing. So if you're the technician, you're more like measure it. But if you're like the mechanic in the backyard under the shady tree working in the moonlight, you'd be like, oh, I know how to diagnose it. You hold the key to crank and I'll go bang on it with my hammer. Pow, 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 pow. And if all of a sudden it works, you've actually done more diagnosis than you might expect. If we had sticking brushes right here and you bang it on it, all of a sudden gets it to work, that tells you, hey, it's in the motor. Go ahead and sell a new starter. Make sense? What special tools? Your friend and your hammer. Right? That was it. No special fancy diagnostic, nothing. Same thing, if it was a fuel pump, I mean, I've even done this. If I go out in the dealership and I go to start the vehicle and it's a crank, no start, I listen, I hear no fuel pump, I think the fuel pump is bad. I've been known to sometimes roll under the vehicle and punch the fuel tank, pow, and get back in. You know, it's helpful if you can have somebody crank it while you punch it, because at that point, we could be sending 12 volts here and ground here, but if the brush is a little stuck and you hit it and it jars it just a little bit and all of a sudden it makes the connection while you're still trying to crank it, giving it 12 volts and ground, it can actually get it moving. And then I can drive the vehicle in, and that way I don't actually have to push the vehicle in. So that'd be mainly the reason, right? So it sounds insane, but there is the way I was taught, which is if it's a bad motor, check for 12 volts, check for ground. If it's got 12 volts and ground, it doesn't work, it's a bad motor. We don't really care if it's the brushes or whatever. But then when I went to work, it was sort of like, you know, a blower motor doesn't work. You go and you put the blower onto 4 and you put the AC on and it doesn't work. And next thing you know, I see a technician in a uniform looking really professional, making a lot of money per year, kicking the bottom of the dash. And I'm like, what the heck have I got myself into? And then sure enough, boom, the motor starts up. And I'm like, okay, what was that all about? It's like, well, if you got a problem inside the motor with the brushes sticking and you bang on it and it starts working, you know it's the brushes sticking, so you might as well just sell the motor. Keep the multimeter, the test light, the wiring diagrams. Keep your pocket protector, highlighters where you're going to trace it. Keep all that in there. Just bang on it a little bit. Sounds crazy, huh?
But how much time could it buy you? Would you like do it every time it doesn't work? You know, do that for a couple months?
I can tell you from firsthand experience. So my wife's dad had a Jeep Cherokee. It was kind of junky. It was you know, you say Jeep, but I mean I'd say heap. The J is silent for me. It's a heap, big old heap of trash. And so she goes out one day to start it. The car doesn't work. Calls me. I'm sorry. It's just the truth. So even though later we bought a Wrangler and she loved it, and then we sold it. But so she calls and says, hey, the car, actually I think her dad called. This was before we were married. She was still living at home. I was trying to do everything right, you know, get off on my best foot, be like, let me make sure I show all my positive traits. Her dad calls, hey, the Jeep won't start. Can you diagnose it? Yeah, sure. Go over after work, roll under there. Just say, hey, all I need you to do is hold it in the crank position. Boom, I measure at the starter. When he holds it to crank, I get 12 volts right here. That's it. That's all I need to know. Your starter's getting power, but it's not working. Your starter's no good. Now, should I measure ground? Yes, but the starter's grounded through the housing, so it's like these don't really lose ground because it's bolted directly to the blocks. I'm like, yeah, you need a starter. And then he's like, oh, should I get a rental car? And I'm like, nah, I'll take care of it like this weekend when I get a little time. Well, what should I do? All right, just hold the key. Bam! Oh, you fixed it. Like, no, I did not. I just temporarily got it going, okay? I don't recommend using this. Now, that last part went in one ear and out the other ear, okay? So I told him, I mean, he kind of got it. He's like, oh, okay, at least we know, like, I can move it around the driveway, but I won't take it to work. Now, my wife, before we were married, okay, we've sharpened each other a little bit on our listening ability, okay? She's like, I want to go to Walmart. This was back when we were in New York, so Walmart was like the big destination. Not New York City, but like small town. There's nothing there. My hometown had a McDonald's. They couldn't get enough business. They closed McDonald's. We didn't even have McDonald's. Like that was like, okay, different times. So she's like, I want to go to Walmart. I'm like, And she's like, well, I started it at work. All right, whatever. She takes the car to Walmart, goes into Walmart, Wally World stuff, does whatever. And it's winter, and there's snow on the ground, and it's cold, and it's dark. And she goes out, and what do you think happens when she goes to leave? Nothing. So she calls, and I'm at work, and I'm like, okay, here's what you're going to do. You're going to go under the car, and you're going to look for the starter. What's a starter? And I'm like, all right. Picture, it kind of looks like a soda can. Look for a thing that looks like a soda can. And then the thing is, you got to hit it. She's like, hit it with what? I'm like, hit it with your purse. And I'm like, no, I don't know. You got to find something that you can bang into it with. And so there she is under the car. I'm of no help at that point. I did tell her, though. I mean, I told her. She did this at her own risk. Her dad understood it, and she's more like, oh, you fixed it. Like, no, I did not fix it. And actually, we got really lucky. A lady's walking by, and she sees these little boots sticking out, and she's like, hey, what are you doing under there? And she's like, I'm looking for the starter. And the lady's like, oh, that happened to my car. I know what that is. So this lady goes and gets a hammer out of her car. Now they're both under the car at Walmart, and they're both looking at me like, I think it's that one. So they're banging on it. She goes up there and tries to start it. She actually got it running in the parking lot. I was pretty impressed. It was totally this other lady who'd been through, some stuff. So she got it running, and this is what I had to explain to her. So I don't understand. It works or it doesn't work. Like, no, listen. Couple things could happen. If the brushes are stuck and you free them up, it'll work until the next time the brushes stick. But the other thing I've seen is if you look at each one of these segments in the motor, you got a positive and a negative, and this winding right here is what's going to get it moving when it's like down here interacting with this permanent magnet. If you had one bad segment in this motor right here, it's only a probability before it lands on the dead spot next time, right? So typically what I'd see is maybe about eight segments in the motor, and if one fails, you got 7 good ones, right? So a lot of times, like probably 7 out of 8 times, it'll work. But then 1 out of 8 times, it happens to stop on the dead spot, and it won't work 1 out of 8 times, and the 1 out of 8 times happen to be in Walmart parking lot. But then when you bang on it, if you can just get it to rock just a little bit, it'll get within the magnetic field to be strong enough, it'll pull the motor over. And once it starts to spin, the 7 working segments will coast across the 1 bad one. But once in a while, the 1 bad one will stop where you really needed it not to stop, and then it won't work, right? So that was kind of like the visual way to understand what might happen. How long can you get by? I mean, as long as you're willing to bang on it, it'll probably keep working. But, okay, unofficially, if you look at this starter, this part actuates the solenoid. This is the actual motor part. Anywhere on this round piece. However, they're a lot more sensitive now when they have these permanent magnets. So if you hit it too hard, you'll break a magnet, and then it can't be remanufactured. Now, to me, I don't care because I don't remanufacture them anyway. But like once in a while, you'll see on the box, like, do not hit with a hammer. Do not do this, because they know we know how to get by. We know how to make it work. but it could cause some damage. But by the time you're going to change it, kind of like, who cares? So in a jam, I get it going. But what happens if you have another one right next to it fail? Then you might be done, right? So it's really a limited amount of time that that's going to work, but I don't know. I've seen it work for a while, like months, like years. Like some of the people I know, you know, where the men are men and the women are too, and the sheep are nervous, like they just keep banging on them and like they just make it work. Nobody wants to fix their cars where I was from. It's rusty, it's nasty, it's just like you just keep getting them by. And we had a lot looser smog laws and stuff. So here people are more conditioned, like you got to put a lot of money into your car, whereas there was like, no, even if the brake lines are rusted and it's unsafe, I'm gonna keep using it, you know. So yeah, maybe you can get by, but it sounds crazy. Sometimes banging on it is a pretty good indication that it's actually the motor. And from there, you just would have to replace the motor, whatever the motor is, fuel pump, starter, whatever. Fun story, true story. Then this kind of shows like what I was saying. You know, you've got these, they'll call this like a pole shoe, and sometimes these are electromagnets, and generally this is an electromagnet. So this is kind of inefficient because we've got to magnetize the stator and the rotor, and that's why we've gone to the permanent magnets. So that way at least we don't have to run field windings on the pole shoe out here, right? So that's overall, generally the main thing that you need to know is the motor needs to get 12 volts in ground, and internally it's going to switch it as necessary. And if for some reason it doesn't, we're replacing it. And that's kind of the end of the story. You could get really into like all the details of the different types of motors. There are a little bit more that you should know. A stepper motor, for example, it's a motor, but it doesn't necessarily just spin. It moves in steps. So a good example of a stepper motor with this would be like your odometer or even your gauges. So when you put gas in the car, you know, the gas was low, right? So from your perspective, the gas was low. When you put gas in the car, the gauge goes up. But how? Well, that little needle that moves, we're actually going to connect that to the center of this stepper motor. And then we're going to use the control module, and we're going to say, hey, it was on E, so that would mean line up right here. But now that you filled it up, we're going to have it run the motor 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps, and that would read full. So your actual gauges move the needles on a stepper motor. The reason that I'd say that that's really good to know, let's say you get a customer car in or your own car, and the gas gauge doesn't read right. Or like recently I had one where the oil pressure needle was like buried past high. And it's like, that's not actually, the oil pressure is not off the charts and spun around and jammed up against the other gauge. So you could actually go in with the scan tool and you can control these stepper motors and get them to sweep. So if you want to know if it's the motor, you go in with the scan tool and you'll say, show me empty fuel, show me 50%, show me 100, 90, 80, 70, 60, 50, 40, 30, 20, 10, 0. You can actually sweep it with the scan tool. If the motor's no good, the sweep won't work. Make sense? But if you go in with the tool and the sweep works and the needle goes to all the correct spots, but then let's say you start the car and it's reading wrong, that would give you an indication that maybe it's on the sensor side, right? So your fuel level sensor sweeps and it measures your fuel. It could be a problem with the arm or the float or the sensor, but it could also be a problem with the stepper motor in the instrument panel. So just knowing kind of how it works is good. And all it's going to do is it's going to send 12 volts in ground to actually move this, and it's going to do it in steps to indicate, you know, fuel level or battery voltage or something. So stepper motors, same concepts. It just doesn't spin. It moves in a step. Kind of simple. And then I believe one of the last things I do for motors is AC. We didn't used to need to cover this, but we need to do it just a bit because DC motors are normal. This is a DC motor. Then when we get into hybrid and EV, The AC motors can be more powerful, lower maintenance, more reliability. So all of a sudden, we're introducing these AC motors in the vehicle, and the AC motor could be the main traction motor, like these. That's the actual motor that turns the axle to turn the wheels. This is the Tesla platform. Or it could also be like the AC. So if you don't like hybrid EV, like I get you, I understand that sentiment, but someday you're in a relationship and your spouse of a sort or whatever is like, hey, if you go into Home Depot, just so you know, I'm running the AC in the car the whole time. And in my Hummer, I'm like, oh my gosh, that's going to be so expensive. But in an EV, you can go to Home Depot, leave, for in my case, her in the car, and she can run the AC without running the engine, because the AC compressor on hybrids and EVs is an AC-driven electric motor compressor, and it'll literally just run the compressor. It's not running the engine, it's not burning gas, it's not using all the gas that was $4 something a gallon, that type of thing. So I'm like, EV and hybrids like pretty nice now. I like that. Cool. The way we couldn't do it before is like this DC motor would have to have huge cables, and I don't know that this would last very long trying to run AC. But with an AC, an alternating current powered AC compressor, it can run your AC all day, and it'll do it off the little hybrid battery. It's very efficient. You don't even have to have the car all the way on. It's pretty amazing. So when we want to do a strong motor that's going to spin fast and be really efficient and run for many, many, many hours, we'll probably change over to AC motor. So the main points about the AC motor for now are just, obviously they use AC. They have a fixed stator, has some coils of wire. The rotor is usually going to contain the permanent magnets. So like with the DC, we usually have permanent magnets outside and electromagnets inside. With the AC motor, it's usually the other way. Permanent magnets on the spinning part, electromagnets on the outside part. Not a real big deal. And they have different types, but mainly if we were to look at this, it's going to be 3-phase most likely. So with a DC motor, 12 volts in and ground. With an AC motor, there is no ground. It doesn't need a ground, because remember, alternating is positive, negative, positive, negative. So the way that you test a DC motor is you check to make sure it's got 12 volts in ground. The way you check an AC motor, you actually have to put your meter on AC and make sure it's oscillating positive to negative, positive to negative. And that is kind of a lesson in itself, and we won't do that in this class. But if you take a hybrid or EV class, we'll definitely do that, because we need to verify that these are correct. And additionally, the AC motors generally are going to be much higher voltage, so we need to test these phases and make sure phase 1 is not shorted to phase 2, or phase 2 is not shorted to phase 3, or phase 1 is not shorted to phase 3. So there's like a little bit of a different way of how we go about testing an AC motor. It's not just measure 12 volts in ground. It's a little more complex. And we can also measure the resistance of each of these windings. So there's phase 1, 2, and 3. And we can make sure that the resistance is good for phase 1, phase 2, and phase 3. And probably that's about as much as I'd like to say for this class. But just understand, I simplified DC motors because they are simple. AC motors, fairly simple, but not as simple as a DC. So if you want to learn more about AC motors, A, I'll give you a little individual lesson, but not for everybody. Or B, the hybrid EV class, you're going to spend some time on AC motors, because that's what we're using for the AC and also for the main movement of the vehicle. Cool. All right, let me make my plan real quick right here, and then I'm going to make our plan for a break. We are almost there. Okay, actually, we're at a pretty good spot. Motors are done. The final concept for electricals right now. Then electronics is its whole next thing. Probably not going to happen today. which is fine. So coils. Ignition coil, for example, is a transformer, but sometimes a transformer is not necessarily an ignition coil, but all ignition coils are transformers, if that makes sense. An ignition coil takes your 12 volts or so, and it makes it into, I don't know, 60,000, 100,000. For now, let's lowball it, and let's just make it 12,000 for fun. You put in 12 volts, you get 12,000 out. That sounds magic. I like that. Why would you want 12,000 or probably 60,000 plus? Well, when you go to spark a spark plug, remember the spark plug has to arc that gap. To jump a gap, it has to have like really high voltage, right? Electrical pressure, more pressure to jump a gap. So when we go to spark the spark plug to ignite the fuel, to do the combustion magic that we have, right? You hate those EVs and electrics. You like ICE, internal combustion engine. You like vroom, vroom. You like these sounds. All that comes from air and fuel compressed, and then we have to spark to start the burning, to start the combustion. The spark has to have high voltage. How do we make the high voltage? The coil. The coil is going to take 12 volts in. That's called the primary. It's going to go around a coil so many times, but then the secondary coil is actually going to generate high voltage. And so this is the part that's a little bit hard to explain. If we have 12 volts going around here, let's say 10 times, and then inside of there we have another coil, a secondary coil, and it goes around 100 times. We were going to go 1,000 times. So if this goes in 10 times, this primary goes 10 times. What's 10 times 10 is 1,000. No, we would want 10 times 12 volts to 12,000. 1,000 times more. Okay. If this primary goes around 10, we would need the secondary to go around 10,000 times. Okay, so there's a ratio there of how many coils go around each one. So the primary is 10 and the secondary is 10,000. That's going to increase 10 volts to 10,000 volts. Okay, that's the ratio. The number of coils causes the increase in voltage. That's what the coil does. So you see the primary goes around in blue and the secondary goes around in red a lot, 1,000 times more. If we send our 12 volts in and it goes around, 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 that's going to make a magnetic field, right? But then what's going to happen is very rapidly, we're going to take the ground away. It's going to generate this nice magnetic field. When we take the ground away, that magnetic field is going to collapse, and the electrons that were in the 12 volt side are going to basically be induced into the secondary side, which is going to make our 12,000. It sounds kind of weird, but in this device, we put in 12 and we get out 12,000, but it's a little bit more to it than that. It's almost like, imagine if you could put $12 into a machine and have it give you back 12,000. That'd be cool, right? You guys should know nature doesn't work that way. That's not how this whole universe is set up. If you put in 12 and it gives you 12,000, it had to have charged you something, right? The coil, you put in 12 volts and it spits out 12,000. So you're going to get 1,000 times the voltage, but you're going to get 1,000th of the amperage, if that makes sense. So you're putting in 12 volts at 12 amps. You're going to get out 12,000 volts at 0.001 amps. Make sense? Why would we want that? Well, we need the high voltage to jump the spark plug gap. So they figured out a way to make these windings in a proportion so you can get 12 volts to become 12,000, but 12 amps is going to become 0.001. And when we pulse the ground, it's going to induce the 12 into the 12,000 and actually fire the spark plug. And we could go into a lot of detail on that, But just understand, a coil or a transformer has the ability to make one voltage a different voltage. And it all has to do with the number of coils in the middle and the number of coils outside. So whether it's a coil specifically, an ignition coil specifically, or any type of transformer, these modify our voltage. They can bring it up, they can bring it down. Like for example, in your home, you're used to running 120 volts AC. From the power pole, you're dealing with, it's kind of like 240, but we'll say 120 to 240 volts. The actual power plant's putting out kilovolts, thousands of volts. You can't use that in your home. So it goes to a transformer, and the transformer steps it down from thousands of volts to 120 or 240, and that goes to your house. Make sense? So these devices increase the voltage or decrease the voltage. If it increases the voltage, it decreases the current proportionally. If it decreases the voltage, it can increase the current proportionally. Okay, so that's how they work. That's the reason that we have it for the spark plug. So like this is it more three-dimensionally. When we have this primary coil outside, that's going to generate a magnetic field. When we suddenly take the ground away, it collapses it, and that moves the current to the inside, and that'll fire the spark plug. And that's mainly, what you need to pretty much know about a transformer. Another example of a transformer would be hybrid EV. You have, let's say, a 240 volt battery pack, but you need it to charge your little 12 volt battery like this little guy. They'll actually do a DC to DC converter, and they'll take 240 volts and drop it down to like 13.8 volts to charge this. So there's examples of devices on the vehicle that coils a transformer, but there's also the DC to DC converter. That's a different type of a transformer. Cool. That process, though, you got to understand, it causes heat, and so like coils, for example, we'll have those up somewhere where they can be cooled, or they'll have a little heat sink, or etc. But so they're not exactly magic. They're going to be pretty much like a coil of wire around another. I actually think I might have had that backwards. It looks like the secondary has fewer coils. Okay, the primary has more. No, this is a step down. I had it right. So the primary would have a lot of coils, and the secondary would have less if it's a step down. The coil we talked about would have less on the primary and more on the secondary, and that would be a step up, right? So they're all kind of, they're all the same, but depending on which way you go, it's all about the ratio of coils on the outside versus the inside. Okay, so other than that, you should be pretty good for now. So I think our plan is going to be, let me pause.